when it comes to vibrant images of celestial bodies and the various celestial bodies that make up our universe, I mean, nobody's got your back like the Hubble Space Telescope. You need an image of the Orion Nebula? Hubble got you. You need an image of the galaxy cluster M0735? Hubble got you. You need an image of the massive star Vi Canis Majoris? Hubble got you. Regular ass Jupiter.
Hey, buddy, thanks for interrupting and showing us that. But you realize Hubble's just a telescope, right? It's just...
Whoa. Just a telescope? Jimmy, if Hubble's just a telescope, then how do you explain this? Yeah. The telescope is called Hubble. Galaxy Cluster 1, Hubble got you. A-Bell 901B, Hubble got you. Birth in the Eagle Nebula, Hubble got you. The remnant of Kepler Supernova, Hubble got you. The dude who sells me shawarma, Hubble got you. Business lady with the chicken parm, Hubble got you. Yo, the tourist from Peru, Hubble got you. A homeless dude with a kazoo, Hubble got you. A rat, holler that squirrel, Hubble got you. Yo, everyone in the world, Hubble got you. Yeah, this is chapter 1 in my 97 chapter epic poem to the Hubble Space Telescope. HST. Unlike any other, you are my brother. Forever telescopic, so don't change the topic.
Hello, and welcome to Astronomy on Tap, number 67. I am Rebecca Larson. I am a PhD student at the University of Texas at Austin. And my co-host tonight is...
Hi, I'm Michaela Bagley. I am a postdoc at the University of Texas at Austin.
So we have a great show for you tonight. And without further ado, let's get started. That's my job. Hang on. Oh my gosh. Aha. All right. So again, tonight it is Astronomy on Tap number 67. So it's our 67th month in a row of doing Astronomy on Tap. We will not be stopped. So we are doing this live to you in your living room. And
this month is also a very special month because, as you gathered from our awesome intro video, it is the Hubble Space Telescope's 30th birthday. So this is our special Hubble birthday edition of the show. And we are here to celebrate everything this amazing telescope has done over the past 30 years.
So 30 years of exploration with Hubble. It has been an incredible journey. There's been so many discoveries, amazing, beautiful images, lots of things that have inspired just humanity in general. And we wanted to celebrate that. And so tonight we're going through and having special talks for you all about Hubble, the results that we've gotten from it, and some of the new things that we can look forward to in the future, all the while celebrating some of our favorite images. So if you would like to join us in celebrating Hubble's 30th birthday this month, please go ahead and share on the social medias your favorite Hubble image and use the hashtag favorite Hubble image, and then we will see those and share those as well. We just want to keep promoting all of the good science and the beautiful images that have come out of this telescope.
Speaking of favorite Hubble images, Rebecca, what is yours?
So everyone has probably seen this particular image that we're showing right here. This is the Eagle Nebula and the Pillars of Creation portion of the Eagle Nebula. And so what you actually are seeing is like dust and gas in space. And inside all of that dust is where stars are being born. And at the top of that left pillar, you can actually see light shining out from behind the dust of those stars that are in there. Being formed, but this isn't actually my favorite Hubble image. My favorite Hubble image is when Hubble looked at this in the optical and gave us this picture, and then went back and looked in the infrared and gave us this picture. And so what you're actually able to do is you're able to look through some of that gas and that dust and see all of those stars that are being formed, see all of the older or redder stars in the background right there, and you still see some of the light from that top pillar there on the left. And to me, this was really meaningful because I was trying to study the universe And I found that you can't just look at one wavelength of light. You can't just look at optical light. What your eyes can see is not good enough to tell you a lot about the universe. And so we need multiple wavelengths. And Hubble was able to add an infrared camera and look at light in the infrared, which is things outside what our eyes can see. And it opened up a whole new universe to us. What about you, Michaela? What's your favorite Hubble?
Yeah, so I had a really hard time picking. I don't have just one favorite Hubble image, as I'm sure most people would have a hard time choosing one of all the incredible things that have come out of this telescope. I'm a little bit biased in what excites me with Hubble. I study some of the most distant galaxies in the universe, some of the early galaxy formation. And so I'm really excited by the work that Hubble does, pushing the bounds of what we can achieve observationally in astronomy, just looking as far back as possible to the earliest sources we can detect right now. And I know we'll hear a little bit more about that later, but that kind of stuff really excites me. However, those images aren't necessarily very pretty. And so I chose this image because what we're seeing here is a picture of two galaxies that are colliding. And we think that many of the galaxies built up their mass in the early universe through mergers just like these. And so what we're seeing here is local, it's in our nearby neighborhood, but it's somewhat indicative of what we think happened a lot in the early universe. And I love the level of detail that we can see. And when we look at galaxies like this, so distant, that whole thing would shrink down into a tiny little blob. So it's really exciting to be able to see with such detail what's going on.
Yeah, I feel you on that one. Our science is very distant, so our galaxies aren't quite so pretty. They're tiny little blobs. And while my favorite Hubble image might be the one of the galaxy I study, it's not very fun to share. All right, but tonight we have a lot of really fun talks. We have first up Dr. Fritz Benedict, who is going to tell us about the Hubble Space Telescope and the whole long roller coaster ride of the lifetime of this project.
Next up, we have Dr. Laura Kreidberg. Apologies for destroying your name there, but she is joining us from the Center for Astrophysics, and we're going to hear from her about exoplanet atmospheres through the eyes of Hubble.
And last but certainly not least, our boss, Dr. Steven Finkelstein, is going to talk about uncovering the history of cosmic star formation with the Hubble Space Telescope and some of the really cool galaxy studies that we have because of this. So of course, as always, science is better with beer. And so personally, I've brought our beautiful pint glass and I've got some beer in it. And I wanted to give a shout out to our venue. We normally host our show on the third Tuesday of every month at the North Door in Austin, Texas. And unfortunately, we can't do that right now. And so we would love to do everything we can to support the people who work there, also make our show possible by bartending and doing the doors and, just giving us food, all of those things. And so if you would normally come to our show and buy a taco or buy a beer and tip your bartenders, if you could, we have a link where we are sending money to those workers at the North Door so that they can live during these difficult times. Those will be in the comments. Those will also be in the description of the YouTube video. So if you feel like you can and you're in a position to help, please help us help them out. Also want to give a shout out to our other sponsors. Odell Brewing Company is our beer sponsor. And unfortunately, I couldn't find any Odell beer at the store that I live next to. So I am not drinking that right now. Shout out to them and shout out to the Austin Astronomical Society for being amazing sponsors and for always showing up to our shows and going on this amazing space journey with us. I guess I already talked about this.
You did, but I just wanted to mention that, so here's the link again to help out the North Door in Pueblo Viejo. And I just want to mention that at our last show, we raised through your help, our audience help, over $400 for the North Door. So that was completely awesome. And we hope that you're able to help out again this month.
Thank you, thank you, thank you. And thank you from the North Door. They were very grateful for your help. And so let's keep that up. So while you are not watching us on YouTube live for our shows these days, you can watch all of our other shows on any of our previous videos here on YouTube. Follow us on Facebook or Twitter or Instagram. Send us an email. Check out the website. We are trying to be as active as possible and to bring you a lot of great astronomy things to keep you entertained and keep you learning during these times. So please give a shout out, say hello. If you have any comments or questions, send us an email or message. And we would love, again, to see your favorite Hubble images. So go ahead and tag us, use the hashtag, and we will share those around.
We are still taking questions as we would during the live show, and now we're doing it virtually. So during the talks, ask questions over Twitter, use the hashtag AoTATX67. You can also ask questions in the YouTube comments. We have people, awesome people, who are checking both of those things and collecting all of your questions. There's no need to wait until the end of a talk to ask them. If something occurs to you, throw it in there and we will find it and ask our speakers at the end of their talk.
Yes, big shout out to all of the people helping behind the scenes that are not on the camera, because this is a lot of things to stare at, and we wouldn't be able to do it without you. I think Caltech, AOTLA is helping us out, and Tucson, Space Drafts is also helping us out in the comments, as well as our committee here in Austin.
We are doing trivia. We have 14 questions, I think, this week, a little bit larger than usual. We've got questions provided by and featuring all three of our speakers. To play trivia, you can go to this link.
That's the wrong link.
Not that link, not that one. Just kidding. I was supposed to update that and didn't. So please use the link in the YouTube video description. Please, we only require an email, but please also add a name so we know who you are, and we will be choosing one or two winners who get a perfect score or the highest score, and then we always choose at least one random winner. So you do not have to get everything right in order to win. So definitely play; it's a lot of fun. Follow along during the talks because the speakers will address the questions during their talks. And at the end of the trivia questions, we have a few additional questions about you that helps us get to know how you heard about the show, what you like about the show, what you don't like, what you'd like to see more of. So if you have some time to fill out those are really helpful for us when we're planning our future shows.
We are giving away prizes. We will figure out a way to mail them to you. I forgot to grab the mug before I did this, but we do have coasters, courtesy of Odell Brewing Company, with our cool little logo and in a beautiful star shape. And we have a purple coffee mug to go along with them for our trivia winners. So there are still prizes. We will mail those to you somehow. So please, if you would like to play and you want to win, include some information so we can contact you. Also, please be kind to each other. This is a very no harassment zone. So please be respectful of other people's in the comments, in the YouTube chat, in questions, virtually on any of the social media. This is a difficult time for everyone, and we want to make sure that all we're focusing on right now is bringing you science and learning and drinking and all of the important things. And so please be respectful and be kind.
And so with that, let's get started with our first speaker.
All right, so first up, we have Fritz Benedict, who is going to talk to us about 40-something years, sorry, I already closed the thing, of the Hubble Space Telescope. So Fritz, we asked you, what is your favorite Hubble image?
And that would be NGC 4314, which I think that one right there, yes. Now, why is this my favorite? It's because I was able to convince my colleagues to let me burn some Hubble Space Telescope orbits on imaging, when in fact the science I do has nothing to do with imaging at all. So this was basically, I can't say it's a hobby, but something I was very interested in doing. And this is a galaxy that I'll talk about a little bit in my talk, but it's a hotbed of star formation only in one place. It's like walking into a town and there's only one bar in town. There's only one place where something interesting is going on, and that's this galaxy right in the center. So I'll talk about it more in a bit.
Fantastic. So thank you. Fritz's information is here on the screen for you. And we will go ahead and let you take it away, sir.
All right, let me see if I can get this right.
You got this.
Did I do it?
Perfect. You're great. Go ahead.
All right, thank you. Okay, so I can't talk about the entire history of Hubble Space Telescope in 15 minutes, so I'm just going to give you some high spots or some low spots. And the clapping was originally a song by the Bee Gees called Staying Alive, because that's what the telescope's done for 30 years, is stay alive, thanks to the brave astronauts who have gone up and serviced it multiple times. So I'm going to talk about two basic topics, some early difficulties, which I remember vividly because at times it looked like I didn't have a job anymore. And then right at the end, I'll just tell you something that keeps going. We keep discovering interesting things with Hubble Space Telescope. So everybody remembers the mirror debacle. Basically, it was the most perfectly made mirror that had the wrong prescription ever. And so they scrambled around, figured out what they had to do, which basically send some people back up to the telescope and install a new camera and some corrective optics. And when they did that, it made it a whole lot better. The science I do with the telescope, it turned out it didn't matter at all. We could have worked with the bad mirror because I work with something called the fine guidance sensors, which hold the telescope steady. And but the telescope wasn't being held steady. So before the first servicing mission, which was in 1993, we had a telescope that looked like this. And those solar panels on either side of the telescope are there to provide power. And they were absolutely horrible solar panels in that they flapped and moved around. So the telescope's going around the Earth once every 90 minutes, and it goes in and out of shadow. So the metal that was holding these panels in place would expand and contract. And there were two different kinds of metal that they used there. And so they would snap, crackle, and pop, and the telescope would wiggle around. And if you're trying to do the kind of astronomy that I do, which was measuring star positions, this was analogous to trying to count crows, all right? So we want to count some crows. There's easy. That's easy to count 3 crows. Now, suppose I'm going to put you in the back of a Jeep with a pair of binoculars and there's a tree off in the distance with a bunch of crows in it, and I want you to count them. So here we go, count them. How many are there? How many are there? How many are there? Right? You couldn't count them. Couldn't count them at all. So fortunately, what they did was the first servicing mission, they took those solar panels, and Kathy Thornton, the astronaut, threw them overboard, and it was the happiest day of my life. They got rid of those solar panels, put some up that are very rigid and don't bounce around at all. And this had several wonderful effects. One, I was able to do my science, and two, you could take all these gorgeous pictures now without them being blurred because the telescope was wiggling around. And there are lots of gorgeous pictures. And well, the HST is getting older, and there won't probably be another servicing mission, but the last one was particularly important because it was the last time we got to go up and actually upgrade the telescope. And this is a guy named John Grunsfeld. He's an astronaut, and he's also an astronomer. And he was on the last 3 servicing missions. So he actually helped me do my science at a great remove because he made sure the telescope would continue to work. Well, back in 2009, in January, there was an American Astronomical Society meeting, and I knew he was going to be there. He's an astronomer. I was going to be there too. I said, boy, I want to meet Mr. Grunsfeld and shake his hand because he's not only has he done it twice already, but he's going up for a 3rd time. So I'm walking down the hall. Here comes John Grunsfeld down the hall. And I come up to him and I said, Dr. Grunsfeld, I want to shake your hand and thank you for what you've done and what you're going to do in the future. And I'm thinking to myself, I bet he's got a grip like steel because those gloves that the astronauts have to wear in space, you have to be really strong hands. I said, well, I better squeeze hard, it'll hurt me. And I think, oh no, what if I squeeze hard and I break his finger and then he can't go on the mission? So what ensued was the most limp fish handshake in the history of two gentlemen shaking hands. I didn't break his hand. He went on, did great work. Finally, about 2 years later, I got to meet him again, and we had a nice manly handshake. All right, so these servicing missions, so important. So we've already seen the pillars of creation. So this is the original picture, and it was wonderful. It put Hubble Space Telescope on the map. It was above the fold on the New York Times on the front page. But when you go up and you do servicing missions, it just makes it a whole lot better. There's the new camera. It's much better than the old camera. And then, as Rebecca showed you, the infrared, you see things that you would not ordinarily see. So here's hotbed of star formation, a wonderful place where we can study that process in some detail. And another one of my top 10 pictures was this original of the jewel box, but then the new, much better. The servicing was very important. It's one of my worries about the James Webb is that there's no way to go service this thing. It's got to work right the first time. All right. So here's a lovely picture of Orion, and you can see Betelgeuse. Everybody worried about a couple of months ago that it was going to go boom. Well, it didn't go boom. It just puffed out a cloud of gas and dust, evidently, made it go dim for a little bit. But there's red stars and blue stars. What does that signify? It signifies generally it's evolved, a star that hasn't evolved. So it's sort of like age. And here's another picture of Orion here with all the clouds of gas and dust that are making up that star formation process. So my favorite galaxy is this one right here. And again, the blue light is from stars that have just been formed. The reddish light or the orangey light, those are from stars that are much older. So it's like candles on a birthday cake. You can tell where the young stars are and where the old stars are. So the question for me was, the star formation is it like a fuse? Did it all pop off at once, or was it like a fuse burning along that ring there? And it turned out it popped all at once. It was just like a cataclysmic event. Bang! All of a sudden, all the stars came on at once. So, again, the reason it's my favorite one is being an astrometrist, which measures star positions. This is something I could do with a camera. And again, I thank my colleagues for letting me burn some orbits with Hubble Space Telescope on this. All right. So what I actually do is I measure star positions, which probably seems like the most boring thing you could ever do, but there's all kinds of interesting things can come of that. And certainly by measuring star positions, you get to keep the telescopes still in space so it can take those beautiful, and it's done with these fine guidance sensors. I call them the FGS. And it lets us measure angles with a millisecond of arc precision. So what's a millisecond of arc? Well, the full moon is 1,800 arcs across. So you take 1 at 1,800 of the full moon and divide that into 1,000 parts, and there's 1 milliarc second. So it's a quarter 1,500 miles away. And with that, well, I was interested in planets around other stars from the get-go. And with astrometry, what you could hope to do, if there's a planet orbiting a planet and the star orbit a common center of mass. So if there's a planet there, the star's going to move. It's going to move around that common center of mass. And so by measuring the position of the star over a period of time, maybe you can see it do a little circle in the sky, and that would tell you there's a planet there. So we tried this with Proxima Centauri, which is the star to us other than the sun, and we came out totally, found nothing. But we looked for companions shorter than 1,000 days. 2 months ago, just 2 months ago, this got announced. A low-mass planet candidate orbiting Proxima Centauri at a distance of 1.5 AU with a period of 19 days. So we missed it, but only because we weren't looking there. And so in April 2020, which is this month, an old dog, me, is doing an old trick, FGS astrometry, with old data. I went back and reworked the FGS, the fine guidance sensor data that we collected from 1992 to 1997. And this is the result. We actually could see the star doing a little circle in the sky because we knew to look at it. I mean, when you're searching a football field for a small coin, it's very hard. But if you know it's between the 25 and the 30-yard line, it makes it a lot easier. to find. So we were able to just find this and determine the mass for that planet. It's a 18 plus or minus 5 Earth mass. It's about the mass of Uranus, or if you're a 7-year-old, Uranus. All right. You say, well, that's nice. And let's go ahead. No, it's stuck. Hello, are you still? No.
You look good. Is there a problem with the slide?
There's a problem with my, let me see, I'm going to try to. I lost my cursor. All right, well, I'm going to have to do this extemporaneous. I have to do it in interpretive dance from now on, it looks like, unfortunately.
I'm not upset about that.
So I'm not either. So the next slide, which I will describe in glowing detail, is a guy using in Hipparcos, which are 2 missions in space that do astrometry. They looked at this star as well. And last month, they published a result that got 12 plus or minus 8 Earth masses. So using completely different telescopes, completely different data, ended up with the same answer we got within the errors, which means that we pretty much know that there's a planet orbiting Proxima Centauri with a period of about 2,000 days, about 5.5 years, and it's about the mass of Uranus. And it's really quite distressing that I can't show you the pretty pictures at the end. But the last thing to talk about was how much longer is Hubble going to last? And they've done some, well, first of all, what could make Hubble not last? What could make Hubble not last is the Earth's atmosphere. It's only up there about 350 miles, and the Earth's atmosphere is kind of puffy. Sometimes it gets more puffy. Oh, look, it's working now. It gets more puffy, and if it gets, then it's going to exert drag on the telescope. And if there's a sufficient amount of drag in the telescope will in fact fall into the ocean, we hope. Now, Rebecca will point to the rear end of that telescope. You can see that there's a little docking ring there. And what they're going to do, long before the orbit decays, and there's a frisbee the size of a 2.4 meter mirror slicing through downtown Chicago, they'll put a rocket up there and do a deorbit burn. It'll end up in the Pacific Ocean on purpose. And at some point, what I really like is to be sitting on a cruise ship, if they actually have cruise ships anymore after this COVID virus. It's sitting on a cruise ship in a hot tub, drinking a Thai, watching Hubble Space Telescope re-enter the Earth's atmosphere. That would be a perfect end to my career. So this graph here that Rebecca's showing you is basically the prediction of the probability of the last time. And in fact, it's got a 30% chance of lasting longer than I do, because according to the IRS, I'm going to drop dead when I'm 97 years old. So these are it's just been fantastically wonderful time to work with Hubble Space Telescope. I've been one of the luckiest people on the planet. It's been an immense amount of paper was published on April Fool's Day. It's one of my colleagues pointed out to me, and but it's not foolish. It's just squeezing some new juice out of some very, very old data, which is also a wonderful thing about Hubble Space Telescope. Nothing is ever thrown away. So with that, I guess I will stop and ask for questions. And I apologize for the.
Thank you so much for that talk. That was a lot of fun. And we all have technical difficulties. That's what.
Oh, this thing froze totally. I don't understand.
You recovered very well.
No, so.
Thank you very much for your talk. We have a few questions.
Sure.
Let's see. So in one of the early images that you showed, there were little notches missing from the upper right corner. Can you tell us why that image was missing?
Yes, it looks like a stealth bomber, doesn't it? So that notch up there is called the budget cut, because there was supposed to be, there's 3 big detectors and then 1 small detector. And that place where there's a notch, there should have been 3 other detectors there, but we ran out of money, so they couldn't pave it with CC. So it's the budget cuts.
All right, yeah, I guess that'll do it. Let's see, Cynthia Shaw asks, the star, you showed when you were looking at Proxima Cen, the star was going in a circle, but where was the planet?
Ah, right. The planet is way off that graph, because that's a picture of the perturbation. So that's showing what the star is doing. So the planet's way off here someplace. Let's see, so here's the star doing its little circle because the planet's going around, right? They're going in it's like a teeter-totter. So the planet's way out there. We don't see the planet at all, at least astrometrically. We see it astrometrically by seeing what the star is doing.
So you're seeing the indirect presence of the planet,
exactly.
The implied presence.
Right. It's
okay.
Gravity.
And we have, let's see, another question. What are you let me see if this is kind of long. What are you looking forward to doing after Hubble, or is there enough Hubble data that you can keep doing research with older Hubble images?
I'm getting pretty old, actually, so it's I'm delighted that I'm still working with Hubble data. After Hubble, I don't know, I get very excited. Very excited about things like the Giant Magellan Telescope. I get very excited about the Hubble Space Telescope. It is highly unlikely that I'll have 2 synapses to rub together to think enough to actually write a good proposal to get any data out of those. But I can deeply appreciate it, and I do everything I can to sell that stuff. So there's this wonderful saying, a civilization is made great when old men plant trees in whose shade they will never sit. So that's what I'm doing.
Nice. Okay, I like that. Excellent. We have one last question, and this is from Alan Winter. How long does it take to process an average Hubble photo?
Well,
good answer. Okay.
Good question. That beautiful picture of NGC 4314, I can't say that knows numbers enough times. A guy named Zolt Levay, who's an artist and an astronomer, is the guy who turned it into a beautiful color picture for me. So I had nothing to do with making that picture, everything to do with collecting the data, convincing people to collect the data. But then I handed it off to Zolt, and he had his palette of colors and turned it into that beautiful picture.
Excellent. Nice. I spent enough time as a grad student working with Hubble data that I can appreciate how long it takes and how nice it is when somebody produces such a beautiful image. Thank you very much for your talk and for joining us. Sometimes we get some questions that roll in after the talk, so if you're willing to stick around, we might have some more for you at the end. But I'm going to ask you at this time to mute yourself and turn off your video, and we will invite up our next speaker.
Well, Michaela, what I'm going to have to do is I'm going to have to reboot. So I'm going to come back to you
okay.
Because my system is frozen.
Whatever you need to do, we'll see you back here in a bit.
All right, thank you. Bye-bye.
Hi, I think you're muted.
Hi, I just fixed it.
Excellent. Yes, I can. Hi. So this is, I'm sorry I'm butchering your name. You'll have to correct me. This is Dr. Lara Kreidberg.
Almost. Kreidberg? Good
Kreidberg.
try.
Not almost, but thanks. So Dr. Lara Kreidberg is an astrophysicist who specializes in the study of planetary atmospheres beyond the solar system. She is a frequent user of the Hubble Space Telescope and has used Hubble data to discover water and clouds in the atmospheres of several exoplanets. She's currently a Clay Fellow at the Center for Astrophysics, Harvard Smithsonian. So Lara, what is your favorite Hubble image and why?
So that's a great question. And so I love Hubble. I use it to study the atmospheres of extrasolar planets, planets outside of our solar system. And we can use Hubble to learn a ton about the atmospheres, but we can't exactly see them the way you would with your eye. And so we actually use artist conceptions, and that's the image that's showed here. And this is a planet that has a very cloudy atmosphere. And so this was an artist's idea of what those clouds might look like.
Awesome. Excellent. And so now, if you don't mind sharing your screen and take it away.
Sure. Oh, it's telling me I need to install Zoom audio. Okay, hold on. Let me try again. How's that?
So we can see your slides, I think a little bit of the rest of your screen, but.
Let me get into my presenter view. Let's see. Let's try that. Is that good?
That looks good to me.
Okay, awesome. So thank you so much for inviting me on the show. I gotta say, this is like the most social thing I've done in a month or so. So I'm having a good time. Cracked open a cold one. This is my enthusiastic audience. Thanks, babe. And I am going to be talking to you tonight about exoplanet atmospheres as viewed by the Hubble Space Telescope.
Hey, Laura, really fast. Your slides are zoomed in, so we don't see the whole slide.
Oh, let me see if I can fix that. I think I see. Let me just pause and try to. This has never happened to me with Zoom before. Let's try new share. Oh, I know what I did. All right, got it. I clicked on the advanced tab. Clearly not advanced. Okay. All right. How about that?
In a second. I'm gonna stop your share and we can do it again.
Okay.
That sound good? All right, go ahead and try again.
How's that?
That looks great.
Okay, awesome. Sorry for the technical difficulties there.
No problem.
Okay, so just a very brief overview of the history of exoplanets. It's pretty easy to do because it's a brand new field. The first extrasolar planet was discovered in 1995, just 25 years ago. And if you fast forward to today, we now know of over 4,000 exoplanets. As of today, I checked, there are 4,151 planets that have been confirmed. And to sum that up, that means based on how many planets, how many stars we've actually searched for planets, the fact that we found that many already means that there are more planets than stars in the galaxy. So on average, each star has at least one planet. This is super exciting. The importance of this discovery was recognized by the Nobel Prize awarded to Michel Mayor and Didier Queloz last year. And just to give you a feeling for the rate of discovery, I'm showing this plot of the number of planets discovered every year. And you can see that not only is that number growing, but the rate of discovery is actually accelerating. So super exciting time to work on this. And we've learned already that exoplanets are totally different from the planets of the solar system. There's a lot of detail on this plot, but I'll break it down. This is showing from bottom to top the mass of the planet, and from left to right how far away it is from its parent star. The different colors represent planets that have been discovered, color-coded by detection technique, and then the planets in the solar system are noted in black. And just to draw your eye to some really interesting stuff on this figure, there's a whole population of really hot planets with orbital periods interior to that of Mercury. Some of them have orbits shorter than 24 hours. So that's a full year of the planet, a complete orbital revolution around its parent star in less than 1 day. There's also a bunch of planets that are intermediate in size between the Earth and Neptune. There's a lot of debate right now about where exactly the boundary lies between a scaled up version of the Earth, a super Earth, or a scaled down version of Neptune. We're all discussing really actively right now what to even call these planets. My favorite term that I'm on the internet now, I'm popularizing this, Neptini. I think it's gonna happen, trying to make it happen. There's also very massive planets that are right on the border between planets and stars. And a whole host of other stuff, planets with very eccentric orbits, planets orbiting 2 stars, just like Tatooine in Star Wars. That's a real thing. Some planets that are so hot that their surfaces are melted into molten lava. These are known as lava worlds. And even some planets that are so puffed up, so low density, that they're actually less dense than cotton candy. And there's a whole region of this discovery space that we have not been able to explore yet. So there's a lot still to look forward as our telescopes and our instruments get more powerful. So for my work, I study the atmospheres of exoplanets, and I do this to learn about how they formed, how they've evolved over time, what they're currently like, what their weather might be. And ultimately, the goal of this work is to try to identify signs of an inhabited planet based on the properties of its atmosphere. So I'm going to teach you everything I know about characterizing planetary atmospheres in about 2 minutes. This is Atmosphere Characterization 101. And the technique is called transmission spectroscopy. And the idea is the following. So if you have a planet that passes in front of its parent star, a little bit of the starlight can filter through the planet's atmosphere and get absorbed by molecules in the atmosphere. Depending on what it's made out of, the amount of light that gets absorbed depends on what color of light is passing through. So there's a wavelength dependence, we would say. And so by measuring how big the planet looks, how much of the starlight it's blocking at different wavelengths, we can back out from that the chemical composition of the atmosphere, some information about the temperature, and also whether there are any clouds or haze that could block the transmission of stellar light. So to give you a more real feeling for what this looks like, this is an image of the Earth from space in the infrared at about 8.6 microns. That's that big white blob is the moon in the background. And if you move to 9.8 microns, you can see that the Earth appears a little bit bigger there. And that's because there's ozone in the atmosphere that is very absorptive. So it absorbs a lot of light and blocks the transmission. So just to flip back and forth between those, you can see that indeed, even for Earth, we see this tiny difference in the apparent size that depends on the wavelength. And so this is the measurement that we are making for exoplanets. Okay, that's one technique. Technique number 2 is called the thermal phase curve. And I have a movie here. Let me see if this works. Okay, so this is for a planet that is tidally locked to its host star. That means it's close in, the star's gravity is tugging on it really strongly. So that means the planet has a permanent hot day side that's facing the star and a cold night side. And what that means is that over its orbit, as it moves around the star, we see different viewing geometries. So here, the hot day side is rotating out of view. Here's the transit. And now the hot day side is rotating back into view. And what we can learn from making this type of measurement is not only what the atmosphere is made out of, but also what the planet's climate is like by studying how its temperature changes. And I should note, we can't actually spatially separate the planet from the star because in general, they're too close together. But what we can measure with Hubble is a curve like the white curve. And so we can use that to infer the atmospheric properties, even though we can't see the planet directly. Okay, so my main instrument that I use is called the Wide Field Camera 3. This was installed on the last servicing mission on Hubble in 2009. This is a picture of an astronaut doing a spacewalk, and if I ever feel bored or just like having a bad day, I look at this and I think there was an astronaut who did a spacewalk to install the instrument, the camera that I use for my work on the Hubble Space Telescope, and how cool is that? And Hubble is, so why do we use Hubble to study the atmospheres of extrasolar planets? Well, there's a couple of reasons, but one of the biggest ones is that because Hubble is in space, our own atmosphere is out of the way. And so we're sure that if we see something like water, that it's coming from the atmosphere of the exoplanet and not water from the Earth's atmosphere. This is an example of raw data from Hubble. The color scale is how many photons come in, how much light intensity there is. And from left to right, this is going from bluer light to redder light. And then from top to bottom, that's actually just smearing out the light. Funnily enough, when Hubble was designed, no one knew about exoplanets. Hubble was designed to look at faint, distant galaxies, not these nearby, relatively bright stars. And so for Hubble, looking at a star that's 30 parsecs away, it's too bright. And so we don't saturate our detector, we kind of smear the light out, and that's why we get this rectangle. For my work, I just download these images. There's an archive where Hubble data is available. This is an old one, so it's publicly available. If you want to download it, be my guest. The data are kind of messy. This is what happens if you sum up all of the light in that rectangle for a bunch of different exposures over time. So this is showing the brightness of the star plus the planet over time from 3 different visits that are color-coded. You can see there's that drop in the middle, but it looks kind of messy. And it turns out if you spend 5 years in grad school, you can turn that mess into this beautiful transit light curve. This is a transit of a hot Jupiter. It's about 1% drop in brightness. Okay, so that is atmosphere characterization 101. That's why Hubble is so special for doing this work. And to finish up, I want to go through a couple of my favorite discoveries that Hubble has made. So the first one I already talked about a little bit is the discovery of clouds in an exoplanet. Now, we know that all of the solar system planets that have substantial atmospheres also have clouds in their atmosphere. And we're interested in whether exoplanets have clouds too. And the telltale signature of a cloud deck is that it will truncate the amplitude of features in the spectrum of the planet. So I have a little cartoon to illustrate this on the bottom. This is the planet radius as a function of wavelength. And you can see that the clouds will cut off the transmission of light below the cloud deck. And so you just have a little feature poking out on top. So if you measure a spectrum that's very flat or featureless, that's a really strong indicator that there's clouds or haze in the atmosphere. And so we did this. We observed a sub-Neptune planet. This one is called JJ1214b. It's about 2.7 times the radius of the Earth, 550 Kelvin. And this is a Hubble spectrum of the planet. And you can see that the black data points look like a flat line. They don't match any of the models that are shown with the colored lines. And we tried every model we could think of, and nothing would explain the measurement that we made besides clouds or haze present high up in the atmosphere. And so we wanted to know what kinds of clouds or haze could make this happen. And they have to be, it turns out they have to be really weird. So the clouds are probably made out of some pretty weird stuff. The temperature of the planet is a lot hotter than Earth. It's 550 Kelvin. And at those temperatures, you would expect things like potassium chloride and zinc sulfide to start to condense. So very, very unusual types of clouds. Not only that, but the clouds have to be really high up in the atmosphere. So this plot that I'm showing, the red part of it shows where the clouds have to be. And then Earth clouds, I'm pointing even though nobody can see, Earth clouds are down marked by the red arrow at about 200 millibar. That's about the altitude of Mount Everest. And so you can see that the clouds for this planet have to be about 100 times lower pressure. So very, very different. Okay. I want to move on now to talk about an ultra hot Jupiter. This is a planet where we observed thermal phase curves with Hubble to measure the climate of the planet. And you can see that the data, the black points here, look exactly like the cartoon I showed a few minutes ago. The drop in the middle is when the planet passes behind the star. And so now I'm going to show the climate map that we made based on this phase curve. And it looks something like this. So the color corresponds to the temperature, and then it's longitude and up and down and latitude on side to side. And so you'll notice these are some pretty big numbers. So the latitude, longitude 0, 0, which is the part of the planet closest to the star, is about 3,500 Kelvin. That is so hot. It's hotter than some stars. This planet has an orbital period less than a day, so it's right next to its star. It's being roasted like crazy. And then you see a very sharp drop in temperature of over 1,000 Kelvin from the day side to the night side. The day side is so hot that we think water molecules are dissociating there, so it's breaking apart into oxygen and hydrogen. And then when it moves back around to the night side, those can recombine. So just a very violent, definitely not habitable exoplanet. The hottest part of the planet is 2,800 Kelvin hotter than Mercury, which is the hottest planet in the solar system. And the last discovery is my most favorite one, and this is a discovery of water. This is for a planet called WASP 107b. It's about the same size as Neptune, and this is its spectrum. So this is the radius of the planet at different wavelengths. And there's that big bump in the middle that corresponds exactly to where we expect water vapor to be very opaque. And so the planet looks bigger there because the starlight can't pass through the atmosphere. And so you get a big transit depth. And so I call this planet the water world because it has a lot of water in its atmosphere. And to put that in some context, like, why is water so special? A lot of reasons. It's thought to be, it's known to be one of the most abundant molecules in the universe. After hydrogen and helium, the most abundant atoms are carbon, nitrogen, and oxygen. So when you have oxygen, you have hydrogen, you form water. On the Earth, water is thought to be necessary for life. Basically everywhere water is present. We see life where there's no water. We don't see life. And so when we think about planets outside of the solar system being inhabited, one of the things we're looking for is water. Hubble has really done amazing work searching for water in the atmospheres of other planets. It's now discovered strong water features in over 20 other worlds, ranging in size from Jupiter to the smallest one now is less than 10 times the mass of Earth. So really pushing down to Earth-sized planets, not quite there yet. And what I'm looking forward to in the next couple of years is when Hubble passes the torch to its successor, the James Webb Space Telescope, which will be capable of detecting water on terrestrial exoplanets. And we'll use all of the know-how and all the heritage that we've built up with Hubble to make sure that we make the most of our James Webb time and find some water on some more Earth-like exoplanets. All right, with that, I will finish up. Thank you.
Thank you, Laura. And I'm gonna just go ahead and knock on wood and take a drink every time everyone mentions James Webb.
Cheers.
Because holy crap, that's gotta work.
Yeah.
We have a lot of questions for you, but
Okay.
I was going to ask if you could really fast, since you mentioned it in your talk, explain what a parsec is for all of our Star Wars fans.
Oh, for sure. It is not a unit of time, it's a unit of distance. Let's just get that straightened out right away. And it is the angle on the sky. I I feel like I'm back on my qualifying exam. The angle on the sky. Okay. If the thing you're looking at is 1 parsec away, it will move 1 arcsecond in the sky based on the Earth's orbit around the sun.
So 1 AU, 1 arcsecond.
Yeah, and it's in light years, it's about 3 light years.
Perfect. All right, so let's jump into some questions. So we have a lot of questions for you. We might not get to all of them. So please, if you guys asked a question, we will try to get to those later on in the show if we can't answer them right now. So we have a question for you from Charlie. So there were planets, he heard that there were planets so dense that they precipitated heavy metals. Is that accurate, or is it just a myth?
That's a good question. We do know of some planets that are pretty high density, some that are consistent with being made all out of iron. And that could happen if you have a giant impact that strips the mantle off of your planet and you're left with a core. But we think that differentiation does happen during the planet formation process. So as it cools, the heavier material can sink to the core. In fact, that happened on Earth. That's why we have iron in the core.
That's awesome and also incredibly terrifying. Along those same lines, we have some questions about would those planets, if we have planets further from their stars, wouldn't the super Earths with thicker atmospheres be habitable if they were further out?
That's a good question. So habitability is like I would say kind of a contentious term, because all of our thinking about it is based on the Earth, which is just our single example. But kind of the canonical idea is that you've got to have a surface and it's got to have liquid water on it. And so the tricky thing about the super Earths is that when you get too big, if you get bigger than about 2 times the radius of Earth, your atmosphere is so massive that as you go deeper and deeper in the atmosphere, the pressure increases so much that you will form like weird water ice compounds before you get to a liquid. And so there probably is some upper limit on how big your planet can be and still be habitable, but we don't know exactly where that is yet. And then the temperature matters too. So you want to be in that Goldilocks zone where water can be liquid. If you are too far away, your atmosphere will freeze out and you'll have an ice planet, an ice ball. And if you get too close, you can have a runaway greenhouse, which we think may have happened on Venus.
So not too far and not too close, hence the Goldilocks zone.
That's right.
Awesome. So do we know what the composition of any of these new exoplanets is? Are they mostly made of rare materials, or is there a way to tell that?
Yeah, so we're working on it. We think there's a lot that you can learn from the mass and the radius alone. It's kind of like if it's your birthday and you get presents that are wrapped, you can guess a little bit based on how big they are and how heavy they are, what it is. And so for planets that are bigger than, like I said, about 2 times the radius of Earth, we know that they have to have a lot of hydrogen and helium in their atmospheres to puff them up. And we can see that with the Hubble observations. We can tell by the vertical extent of the atmosphere that it has to have a lot of hydrogen and helium. For the smaller planets, we just don't know yet. I would say based on, you can make some guesses based on what building blocks are available. Like after hydrogen and helium, you've got a lot of carbon, nitrogen, oxygen. And so I would be very surprised if a planet had like a pure xenon atmosphere or something crazy like that. Like there's just not that much xenon around compared to all the other building blocks.
So it's a combination of material available and likelihood of being trapped in like an atmosphere or something like that.
Mm-hmm. Yeah.
So we have one more question for you for now, and then we're going to move on. So the last question is, doesn't the spin rate of the planet affect how much it heats up on the day side and cools on the night side? And if you don't know the planet's spin rate, how can you account for that in your observations?
Definitely. That's a great question. So a lot of the planets that we look at have very short orbital periods. So they're right next to their host stars. And in that case, the gravitational pull from the star is so strong that the planet becomes tidally locked very fast. Once you move out to orbital periods of like 10 days, something like that, then the tidal locking is not known for sure. And so, yeah, it's like if you had a planet that wasn't tidally locked, that would really smooth out the temperature contrast between the day side and the night side. And that's something we could potentially see.
That's cool. Do we think we'll be able to do that with James Webb?
If they give us 10 days of James Webb time, sure.
Oh my goodness. What we could all do with 10 days of JWST time would be amazing.
That's real.
Awesome. Well, thank you so much, Laura. We have some more questions for you. If you're able to stick around at the end, and then we'll try to get to those later.
All right, my pleasure. I'll try to stick around.
Perfect. Thank you so much. You can find information for her. We've posted some links for her website and for her Twitter handle and information about her talk and her favorite image in the comments. Those are also going to be in the YouTube description. So check those out when you get a chance. Bye, Laura.
Bye.
All right. So for everyone's favorite part of the show, at least my favorite part of the show, we have Jackie and Danny going to give us some astronomy news. And first off, we did ask everyone who is here on the show tonight what their favorite Hubble image is. So Danny, do you think you could let us know what yours is?
Yeah, so this one is my favorite for no real scientific reason other than I think it's just really cool. For regulars of the show, you know I have a little bit of thing for the moons of the outer solar system, and I just love this this image of Jupiter where you can see some of the moons going from the upper right, Io, Callisto, and Europa. You can see them transiting Jupiter here. And I guess scientifically it is kind of cool because it's an interesting little insight into how we could use something like Jupiter's moon system as like a analogy for how we would study extrasolar planets. But I don't know, it's Jupiter and its moons, so.
I mean, what more can you
That's all I need.
So pretty. So Jackie, what about you? What is your favorite Hubble image?
Oh no.
Oh, you're muted. Hang on.
Okay, can you hear me?
There we go. Yay!
I'm a technical genius.
We're doing
Okay.
great. Everything's fine.
Okay, so my favorite image is of this Einstein ring, and this holds some sentimental value for me because it was actually the image that inspired me to change my major to astronomy. And that's because I got to see it when I was a freshman taking an astronomy seminar, and we learned about this cool thing called gravitational lensing. So this was something predicted by Fritz Zwicky, not the Fritz that you just met, but Fritz Zwicky and Albert Einstein. They predicted that the gravitational potential of massive objects could distort the fabric of space-time, which would create this spectacular light bending effect. And then this was confirmed when Hubble started seeing these beautiful perfect alignments. So gravitational lensing will cause some bending of light, but if you get a galaxy directly in front of another one and you catch it just at the right angle, you get this Einstein ring. And I think this is just the most beautiful example of that. And it's so cool that Hubble can see those.
I love it. This is also one of those really inspiring, amazing images that includes a lot of science and a lot of fun. All right. Okay, I'm gonna go now so you guys can.
Okay. So let's get this news started.
All right. Hi, everyone. Obviously, I just talked to you 5 seconds ago, but just in case you forgot who I am, I'm Jackie, also known as Whataburger Jr. I'm a grad student at UT Austin, and I am here to tell you what's been going on in space over the last month while we've been stuck in our homes. So first, we're going to start off with a comet. So if you were an interstellar comet, you may find yourself in a beautiful solar system with a beautiful coma, and you may ask yourself, well, how did I get here? And astronomers are asking themselves the same question after the discovery of the first 2 interstellar objects to be seen visiting our solar system. So first there was the famed Oumuamua, or as Rihanna prophetically sang, Oumuamua, what's my name? Which was discovered in Hawaii in 2017, and Borisov, which was discovered in 2019 by an amateur astronomer in the Ukraine, using a telescope that he built himself. So if you don't emerge from this quarantine having discovered a new interstellar object, what are you even doing? I'm just kidding. I've spent the last month playing Wii tennis and not discovering anything at all. But anyway, Borisov is classified as a comet, and it's about 14 times the size of the Earth. It's racing at a breakneck speed of 110,000 miles per hour, and the only observatory up to tracking it would be space-based, and Hubble did not disappoint us. So in the image you're seeing on the left, this is a time-lapse image that Hubble took. And the background stars are actually streaking through it over the course of 7 hours as Borisov is hurtling through our solar system. And Hubble has given us the ability to determine its size and shape. And we've even learned that it's actually losing mass as it travels, since it's about 0.4% less massive now than when it was first observed. But it wouldn't be Astronomy in the News with Whataburger Jr. if I didn't mention the best ground-based telescope in the whole universe. I said ground-based, so Hubble still gets a title, but recent observations from the Atacama Large Millimeter Array, also known as ALMA, in Chile, reveal signatures of carbon monoxide and hydrogen cyanide, which is what you're seeing over on the right here. So this kind of astrochemistry allows us to compare interstellar comets to ones formed in our own solar system, like in the Kuiper Belt, to investigate formation pathways. And of course, as in everything with astronomy, one answered question leads to 1,000 unanswered ones to keep us up at night. So astronomers found that the concentration of carbon monoxide was up to 20 times higher than comets in our own solar system, suggests that it formed in a different area than our Kuiper Belt, and it likely had extremely high concentrations of carbon monoxide ice, which chills out at a balmy minus 420 degrees. It was probably kicked out of its young planetary system at an extremely high speed, so it went yeet right out of that system, and it probably formed on the edge of a protoplanetary disk. So what's cooler than being cool? Ice cold, just like Borisov is.
Wow. An ALMA reference. We got 1 on the yeet counter. All we're missing is some talk about how radio dishes on the moon would help out here.
Oh, just wait.
Okay, next up. So if you've been bored in quarantine at all lately, which I hope you're not bored now that you are watching some astronomy, I figured here just do a little bit of magic to entertain you, right? So we have a star that we've observed, for over 15 years, and it had a planet that has since disappeared, okay? Now, unlike all good magic tricks, well, illusions actually, we'll tell you the secret behind this one. What we saw likely isn't a planet at all. So back in 2008, using data actually from the Hubble Space Telescope, people discovered a planet around the star Fomalhaut, which is a star 25 light years away, and it's actually one of the brightest stars in the sky. And this star is interesting. It has this big debris disk, which you can see in the image on the left. And it was theorized that the inner edge of this disk would be carved by a planet. And so sure enough, if you look in the image on the middle, they found a bright point source of light that seemed to be a planet, which was really cool because this was the first time that we had directly observed an exoplanet in visible light. Now, since then, Fomalhaut's had a little bit of a tough go of it, unfortunately. Follow-up observations in the infrared didn't see it, which was surprising for a planet and meant that it was probably less massive than expected. Its orbit didn't really jive with the idea that it was carving the disk, so well, that's pretty bad for Fomalhaut B. But then reanalysis of data in 2012, we're like, nope, we have better techniques now. This data is good. That is a planet. But then, of course, as you might expect, there has been another turn in this planet's little story. Additional Hubble data up through current day has actually shown that Fomalhaut b, the supposed planet, has both faded in brightness and expanded in size, which, I mean, I don't know. I look around at our planets in the solar system. I don't see any doing that here. So that probably isn't a good thing for a planet to be doing. So what's actually going on? Well, a recent study by two astronomers, Andres Gaspar and George Ricci at University of Arizona, actually believe that it is not a planet, but what happened is in this massive debris disk, planetesimals, so kind of the building blocks of planets, two large ones, collided and exploded. And what we're seeing is a cloud of dust that is now dissipating. And this model can explain why this exoplanet is fading, getting larger, and why its orbit seems really weird. So unfortunately, of course, it's sad to have to say farewell to any supposed exoplanet, but it is really exciting to be able to observe the results of one of these stellar debris disk collisions, and this system will continue to be a top target when James Webb launches. Rebecca, you can go have another drink, which will search for actual planets in the system and also try to go even deeper down from its debris disk to see the analogous asteroid belt in this system. So unfortunately, farewell Fomalhaut b, but I mean, hey, even things that aren't planets, Pluto, can still be somewhat interesting.
Pluto's just a dwarf. He's still out there. Also, I'm really sad that you took out the draft I had in your slides, which was Nancy Drew in the case of the disappearing planet. But I just decided to throw that in anyway. Okay, so number 3, we are talking about one of our own, Sinclair, that you may remember, who was my predecessor for the news. And around these parts, we keep it classy. And some may even say it's super classy. Our very own Major Merger reports for duty with her newest paper published in the monthly notices of the Royal Astronomical Society, which includes a massive catalog of over 200,000 galaxies in a 1.5 square degree field. So in comes superclass, an extragalactic field about the size of 10 full moons on the sky. And you heard that right, there are 200,000 galaxies in there. And it's a lucky patch of sky indeed, as it is home to many galaxy clusters around redshift of 0.2. And this makes it a cool place to look for the effects of weak gravitational lensing. So I was talking about really strong gravitational lensing when I showed you that beautiful Einstein ring, but you can also have a weaker effect where massive galaxies will cause a slight bending of the light coming from objects located behind them. And so you need really high resolution observations to see them because it's a pretty subtle effect. But the first thing to do for the observations in this field was to fit photometric redshifts to these 200,000 galaxies. And that involves very careful extraction of the light from galaxies at different wavelengths using imaging rather than spectroscopy. And you can do a fitting technique to determine where they are in 3D space or what their redshift is. She did this using data from the Subaru telescope in Hawaii, as well as the Spitzer Space Telescope and E. Merlin, which is a wizardly radio interferometer located in England. So not quite the moon, but rural England, it might as well be the moon. So the images you're looking at on the left show some of this optical imaging from Subaru, and that is what you're seeing in the purple and yellow. And we see clean detections of 2 example galaxies. But when you take a look at the black contours overlaid, now we're looking at the radio, which is an ever mysterious regime of astronomy. And we see big differences in their morphologies. Some are simple and some have these like huge lobes or outflows. It could be an active galactic nucleus. I actually have no idea. That's not written down anywhere. I don't know why I said that. No one hold me to that. So moving on. All we know is that there are differences in morphologies, which is suggestive of evolution of galaxy structure across cosmic time. But since it's Hubble's birthday, we can't let another telescope steal the light, even though I would love to just talk about radio for the rest of the night. But Hubble has been chugging along for 30 long trips around the sun, and she's not done yet. While Subaru is great for the optical detection of these galaxies, it doesn't have high enough resolution to compare the spatial structure of these galaxies to the detail that you're seeing in the radiomorphology. And that is what our friend Major Merger hopes to tackle before the end of her PhD, kind of a major cosmic question. And so we've just received word that, in fact, the advanced camera for surveys aboard the Hubble Space Telescope has been taking a good long look at superclass for us. And that's what you're seeing in the middle there. And maybe you're jealous that I have such good insider information, but have no fear, because you too can follow the Hubble Hubbub, or the Hublub, on their live Twitter account, Space Tele Live. It updates each day with what it's currently looking at in the sky and what lucky scientist gets to receive those images. So congratulations to Sinclair on your super awesome paper, and we're eagerly awaiting these results from Hubble.
I do love the Hubble Twitter account. So only fitting that in a month where we have a news story about yanking a supposed planet's planet status away from it, we have a story about giving planet status back to a previously thrown out discovery from a recent study led by actually one of our own here at UT Austin, Andrew Vanderberg, who has confirmed the existence of an Earth analog habitable zone planet in Kepler data that previously was thought to not be a planet. So the Kepler mission, the main Kepler mission, the little telescope that could, stared at the same patch of sky for over 3 years, observed many, many stars, continuously looking for little dips in their brightness. Basically, the idea being, if a planet is there and passes in front, it'll cause a dip and you can observe it. And you're observing so many stars for so long, you should find many planets. But you find many planets and you find even more dips that aren't caused by planets. They're false positives. And well, I mean, yes, as a grad student, I do look through data by eye very regularly. I think we can all agree it's sometimes better to leave it to a computer. And so algorithms on computers have been written to search for these dips and classify them as real transits or not. And so as awesome as computers are, actually our eyes are a little bit better than computers at this. And sure enough, on re-examination, Kepler 1649, an M-dwarf star, so a star much less massive and much more red than our own sun, had a false positive that was then looked over by eye and determined to be a real planetary signal. Now, this is really cool just for knowing that, hey, Kepler is still producing so much good science, but it's even more interesting because this planet is an Earth analog, meaning that it's the size of Earth and it sits at a distance from its host star such that it should roughly be the same temperature as Earth, meaning liquid water could exist on its surface. Now, this planetary system doesn't end there. It also actually has a Venus analog in it as well. So another Earth-sized planet, but about half as close to its host star. So this is really interesting, right? We have this newly found system that is analogous to our own solar system. Now, that's not quite 100% true. If you remember what I said, the star is smaller, much smaller than our own sun, meaning that it emits most of its light in the infrared and it's very, very active. It has a lot of stellar winds being shot out from its surface. And so we still don't really know if planetary systems around M-dwarf stars would be habitable in the sense that we think Earth would be. But still, finding these planets in the habitable zone around such stars is the first step to knowing that. And so, you know, this is really cool. Maybe it'll even inspire me to leave a little less data sitting on a hard drive, not to be looked at for years, knowing that cool discoveries await. But regardless, it's really nice to know that even as computers take over the world, the human eye is still good for at least one thing.
I can't believe when the talking heads said there's water at the bottom of the ocean, they were talking about Kepler 1649c. Okay, so now for not in the news, Hubble's greatest hits. extragalactic edition. So finally, we would like to highlight some of Hubble's greatest hits over the years. Hubble has worked tirelessly, taking observations nearly 24/7 since its launch in 1990. And though it hasn't come up with a cure for coronavirus, it has advanced human knowledge far beyond our wildest dreams. When I talked to my best friend about the fact that we were doing a Hubble's 30th birthday show, she said, wow, she is 30, flirty, and thriving. And I can't agree more. So first up, we have the Hubble Ultra Deep Field. So we stared into the abyss, and the abyss stared back in the form of an unfathomable number of galaxies. Not to be confused with UT Austin's stellar softball team, the Ultra Deep Fielders. This is one of the most famous Hubble images. So taken in 2004, this is an extremely deep exposure taken with the optical filters on Hubble, centered on the constellation Fornax. It's only 2.4 arc minutes to a side, which is less than a tenth of the size of a full moon, and it contains over 10,000 objects. It has since been followed by images in the near infrared and ultraviolet, and it's offered us one of the richest fields for follow-up observations. Some of the most distant high redshift galaxy candidates, which are being observed at a stage of formation less than 1 billion years after the Big Bang, have been seen in this field, as well as the most distant resolved star, which happens to be a red dwarf. Number 2 on the bottom here is Abell 2537. So we stared into the abyss, and the abyss looked like a clown house. Among Hubble's greatest hits are its images of galaxy clusters, which are the most massive gravitationally bound structures in the universe. And this particular one is located about 3 billion light years away in the constellation Pisces, and it displays this gravitational lensing effect once again. So it is the warping of space-time by massive objects. So clusters contain so much matter, both light and dark, that their gravity magnifies and distorts the light from objects behind them, making otherwise too faint galaxies easy to pick out with the naked eye, which has led to a lot of high redshift discoveries. So that's really cool. So I probably wouldn't worry about the couple of pounds we're all putting on during quarantine, because you still aren't massive enough to bend light. So at least there's that going for you. And last but certainly not least, Hubble helped us discover the expanding expansion rate of the universe. So the most distant type 1a supernova displayed the discovery of dark energy. So one more time, we stared into the abyss, and the abyss kept getting bigger. So awarded for their efforts with the Nobel Prize in 2011, astronomers Saul Perlmutter, Brian Schmidt, and Adam Rees used Hubble to view the most distant type 1a supernova, which is the explosion of an old compact star. And so you're seeing way zoomed in on this galaxy here. You can actually see the supernova going off. So supernovae are often used as what's called standard candles, because they're so predictable in their brightness that we can use them to determine our distance from them in a really precise way. So in a universe that is expanding, but it's slowing down or is constant in expansion, more remote supernovae would be a little bit dimmer than closer ones. But these astronomers instead found that distant supernovae were way dimmer than their assumed distances predicted, meaning they were even further away. There was no other explanation but that they must be further away than we thought they were. And that must mean that the universe is getting bigger, and it's getting faster at doing so, which is leading to the theory of dark energy. So those are just a few of the most amazing discoveries Hubble has made, and we're not done yet, because now it's time for Planet Edition.
Yeah, but I mean, dark energy, it's important or whatever, but you know, Hubble gave some love to planets as well. And so starting from the beginning, quite literally the beginning, planet formation, Hubble contributed a lot to our understanding of how stars and planets form. Of course, there is the beautiful image of the Orion Nebula, the Orion region, one of the nearest, most massive areas of star formation in our galaxy. And Hubble stared and resolved hundreds of protoplanetary disks in the region, showing that these areas of planet formation are everywhere in these star-forming regions. And Hubble actually even looked in detail at some of the disks. Specifically, you see a few there. Some of the ones that they looked at, they saw gaps and such, right? I mean, everyone always thinks of that beautiful ALMA image of HL Tau, but hey, Hubble did that too. So props to Hubble. Hubble also observed, they did the largest survey in visible light for debris disks. So if you think back to the Fomalhaut story, these disks that remain after planet formation is done, where planetesimals are colliding. Hubble expanded our knowledge greatly on how disks evolve after stars form. Moving on to more evolved planets, and we had a wonderful talk from Laura earlier about Hubble and planetary atmospheres, but Hubble has observed a lot of exoplanet atmospheres, including the first exoplanet atmosphere detected. It was sodium in a planet larger than Jupiter, so it's not quite applicable to Earth, but still really cool. And since has done a lot of important observations, moving ever so slightly closer to our hopes of observing the atmosphere of a habitable planet. In doing so, there is an artist's rendition of the TRAPPIST-1 system, the 7-planet system that took the world and my AoTATX space cadet name, it's a TRAPPIST, by storm. Hubble stared at some of the planets in the star's habitable zone and actually didn't really see an atmosphere, which is a good thing. If it did, it would have implied that it had some hydrogen-rich big envelope that would almost certainly preclude any life from existing on the surface. So in this case, Rebecca, get your drink ready again. Hubble has laid wonderful groundwork for the atmospheric studies forthcoming for this system by the James Webb Space Telescope. And okay, so Whataburger Jr. has ALMA, and again, it would not be astronomy in the news if I could not talk even more about icy moons in our solar system. Much closer to home, Hubble has done some amazing work in the solar system, including finding geysers erupting from Europa's surface, potentially providing access to its interior ocean, right? Europa is a moon around Jupiter that has this massive global subsurface ocean that we think could be habitable. If anyone who knows me, they know Enceladus is another moon with a subsurface ocean and a big plume, has my heart, mostly because of that plume, but Hubble has given me reason to like Europa a little bit more by finding these geysers erupting from Europa's surface. So there are just a few highlights for planets from Hubble. Happy birthday, Hubble. And I think that's it for the news.
Thanks, everyone.
Thanks for tuning in, and we'll see you next month.
Thanks, guys. I'm going to go ahead and just chug a few of these since you keep mentioning it.
Yeah, I made sure to get James Webb in there as much as I could.
Oh, Jesus Christ.
I'm sure Steve and Michaela are joining you on this one.
Yep. All right. Thanks, Jackie. Thanks, Danny. You guys are freaking amazing. That was beautiful and inspiring and freaking hilarious. So stick around. We have some questions for Jackie and Danny from the chat. So we'll again get to those at the end of the show so that we can do that all together. So next up, Michaela and I decided to do this introduction jointly. Oh, hi. We have our boss, Dr. Steve Finkelstein, who is going to give us a talk about galaxies with Hubble. And so I believe your kids are there right now, Steve.
Oh yeah, they're here.
Hi, Maisie. Hi, Karen.
Hi. Hi.
Are you guys going to help give a talk?
Uh-huh.
No, just the intro.
No. So Steve is a professor at the University of Texas at Austin, and he studies distant galaxies in the universe, and likewise, so do Michaela and I.
Steve is also a leader of the team of one of the teams that will have some of the first access to JWST. He'll be helping us teach everyone how to use the telescope so we can get the most out of it that we can possibly. But he also promises that he super loves Hubble.
Definitely.
Hubble is not done yet. All right, Steve. So we asked you before, what is your favorite Hubble image?
All right, you ready to introduce it? Go ahead, Kieran.
My dad's favorite image is the Hubble Ultra Deep Field.
Because, Maisie?
Because it shows that the empty sky is full of galaxies.
Yeah, because the empty sky is full of galaxies. So
and my dad is wearing Hubble's Ultra Deep Field.
That's right. It's the image so good that I'm wearing a shirt out of it. Although I can't claim credit for this shirt. This was made by the creator of Astronomy on Tap, MC Heisey, Rachel Livermore. She gave it to me as a parting gift. But I wear it every day, I promise. All right, I'll see you guys later. Scram.
All right, perfect. So I think you are free and you are ready to give a talk. So let us know, what has Hubble done for galaxies in the past?
Thank you. I am free, and maybe they'll be in bed when I'm done. We'll see. I had to show, because this came up, this is not the only, well, actually it is the only ultra deep field show. So I think Jackie or Danny mentioned the department softball team. This is our jersey, and one thing you might notice, we're called the ultra deep fielders. This is not the Hubble ultra deep field. This is the Hubble deep field. And in my talk, I'll talk about the differences behind these. I couldn't tell if this was like an ironic joke or if Joel Green from last month's Astronomy on Tap, who is not a galaxy astronomer, just didn't know the difference between the two images.
We're going to call him
to this day. The only other thing I wanted to do in this room was advertise, support your local breweries. I'm drinking my favorite beer, Pint House IPA. Of course, it's an IPA. I'm sure Rebecca is not drinking.
I am not drinking an IPA, but I do have local beer. It is a Live Oak Hefeweizen, and it's a Hubble image koozie that we.
Oh, cool. Yeah, mine it has no koozie. All right. So, can we see this? Okay.
You're good.
All right. So today I am, of course, going to be talking about the Hubble Space Telescope, and the journey we'll be going on is looking at the history of cosmic star formation. And specifically how I'm going to fix one thing really quick, how the Hubble Space Telescope has done a series of observations that have brought us through those deep fields. I forgot, I have to put up my background, which my kids would not have shown through. So there we go. All right, so let's get going. So we talked about this a little bit, but I wanted to just kind of hammer it home a bit, remind you there are several reasons why we actually need space telescopes. And so the first one is that when we are looking through our atmosphere, the atmosphere makes things look blurry. And so this is showing you an example on the left of a region of the sky, including a bright star viewed with the ground-based telescope. And the one on the right is that same star viewed with the Hubble Space Telescope. Are we seeing this? Are we seeing this okay? I don't know if we are. There we go. Now we should be seeing it okay. Now are we seeing it okay?
Your screen, yes.
There we go. Okay, sorry about that. So left, star seen from the ground, right, star seen with the Hubble Space Telescope. And you can see that when you go through the atmospheric blurring, you lose a ton of information that's actually there. And so it lets you see deeper, it lets you see more structure. Another reason, humans are awesome, but we're also very bad because we like to see at night. And so we put up lots of lights. And so this is a beautiful image of the Earth taken at night. Not all taken at once. You can think about that and figure that out. But it shows you that people live in a lot of places, and where we live, we put up lights. And when you go into space, you simply don't have to deal with that. You just look away from the Earth. This is one of our favorite places, including Rebecca and Michaela, the Keck Observatory on the summit of Mauna Kea. This is an image taken on a night when it's not so nice to observe. So you may see lots of fabulous sunset images from observatories with these beautiful pink and yellow clouds. Every single one of those images means not a lot of great observing got done that night, because when there are clouds, we can't see to the stars and galaxies. And again, when you're in space, you don't have to deal with that. And finally, as has come up a couple times tonight, not all wavelengths of light actually make it to the ground. In fact, most wavelengths of light don't make it to the ground. So this is a handy chart that shows you from high energy light, from gamma rays, X-rays, ultraviolet, visible, infrared, radio. And you can see these arrows, they kind of show you how far they get. Most light doesn't make it to the ground, just the visible, a little bit of infrared, and the radio. And that's good. Our atmosphere absorbs things like gamma rays and X-rays, which are harmful to living beings. So we're happy about that. Same thing with ultraviolet. But if there are very cool astrophysical, lots of astrophysical information we can get if we observe in the gamma rays and X-rays, likewise in the infrared, which also doesn't make it all the way to the ground. So all reasons to observe into space. So what do the other wavelengths actually give us? Well, there's a lot of stuff, including things like learning about the atmospheres of exoplanets. I, of course, care about galaxies, so I'm going to talk about galaxies. And so when we look at a galaxy in the optical, this is actually a Hubble image. I'm kind of cheating here, but this is something that is doable from the ground, maybe not quite this sharp, but you can see these wavelengths. And you can see where the stars are, but you can see there's these dark bands, and that's dust blocking the light from some stars. If we look in the ultraviolet, we're seeing where only the young stars are. And so this is an ultraviolet image, which is impossible from the ground because the atmosphere absorbs all of the ultraviolet light. And so if we want to see where the youngest stars are, we have to go to space. If we want to see where all the stars are, we also go to space, because now when we look in the infrared, we can actually peer through the dust, much like that Pillars of Creation image that Rebecca showed earlier on. When we look at the infrared, we can peer through the dust. And some of this infrared light does make it to the ground, but as I'll show you in a second, the night sky actually glows very brightly at infrared wavelengths. If your eyes could see infrared wavelengths, you would go out at nighttime and it would look, just as bright as daytime. And that is clearly not a good situation to see really distant galaxies. Why do I care about the infrared so much? And I forgot to mention, Hubble can of course do all of these, and we'll get to that. But why do I care about the infrared so much? Well, we have to go back about 100 years now to the discovery from Edwin Hubble, the person, that the universe is expanding. And so this is Edwin Hubble's actual plot showing distance on the horizontal axis here versus velocity here. And as you go farther and farther away, galaxies are moving faster and faster away from us. And so the universe is expanding, everything is moving away from us. And when we combine that with another property of physics, the Doppler effect, which is that when things move towards you, they look bluer than they normally are. And when they move away from you, they look redder than they normally are. That tells you that when you observe galaxies that are moving very quickly towards you or very quickly away from you, you're going to need to look at different wavelengths. And so because everything is moving away from us and really distant galaxies are moving away from us really quickly, if we want to see their ultraviolet and optical light, we actually have to look into the infrared because it's all been stretched and shifted into the infrared. So long story short, infrared light, very important for distant galaxies, very difficult to do from the ground. And the reason why it's difficult to do from the ground is again because the night sky glows in the infrared. So this is what's called a spectrum. This is showing the brightness versus wavelength, not of some cool exotic object, but of the Earth's atmosphere. And so you can see that in optical light over here on the left, there's not a lot going on. It's pretty faint. But as you go into the near infrared and then into the mid infrared, there's all these spikes. These show emission lines from molecules in our atmosphere, molecules made of oxygen and hydrogen, and they glow very, very brightly. And that makes this kind of work hard to do from the ground. This is one of the best, if not the best, near infrared image taken from the ground. This was taken with the VISTA telescope, a 4-meter telescope run by the European Southern Observatory. And this is the best infrared image taken from space from my shirt, from the Hubble Ultra Deep Field. And this is a different region of the sky, so there's no one-to-one correlation from galaxies here. But on the left, you could count the number of galaxies pretty quickly. On the right, you can see there's a whole lot more galaxies waiting to be discovered. In fact, on the left, you can really only see the brightest things. So if we want to see the faintest, most distant things, you got to go to space. Hubble got you. All right. What does the sharp imaging of Hubble get us? If we can get above that atmospheric blurring, what can we see? A whole lot of pretty awesome galaxies. So I'll just show you a few examples from what we call the local universe. So these are things that are relatively nearby. This is the galaxy NGC 1300. It's a beautiful barred spiral galaxy. One of the things we can see is this sort of hazy blue light, and the blue points, those are massive young stars. And the red little points here in those spiral arms, those are regions of massive star formation. And so this galaxy is forming a ton of stars, but that yellowish kind of bulge in the center or bar in the center, that is showing you where some of the older stars live. So we have a galaxy with a lot of star formation here. And there's a galaxy like M87, which is a honking big galaxy fairly nearby to our own Milky Way, where you don't see any of that blue or those blue or red knots, showing that this has very little star formation. It is doing something weird in the center. You can see this jet coming out. There is actually a supermassive black hole in the center of this galaxy that we've now taken an awesome image of with the Event Horizon Telescope, and it's blowing an energetic jet of material out from it. That would be really difficult to see this awesome resolution from the ground. And sometimes galaxies run into each other. These are the antennae galaxies. There's actually 2 galaxies here that maybe once upon a time looked like NGC 1300, but as they pass close to each other and slam together, gravity has completely distorted their shapes, their morphologies, and it's also caused all of the gas in these galaxies to run into itself and stimulate rapid gravitational collapse and formation of stars. And so in NGC 1300, you could see those red dots. Maybe you can't on your TV or your computer screen. They're very, very small and faint. Look at the size of the red dots or those pink pearls in this galaxy. There's tons of ongoing active star formation here stimulated by that galaxy merger. And so just from these beautiful images, we've learned a lot. Nearby galaxies are very diverse. There are these beautiful spiral galaxies like our own Milky Way. There are these glorious ellipticals, enormously massive, but they haven't formed stars in a very long time. And then there are things like the antennae, kind of messy, irregular galaxies where maybe they've been disturbed or maybe they just never formed a structure like a spiral or an elliptical. So if we take a census of the nearby universe and add the total amount of star formation together, imagine we counted up all those little red dots or pink dots, we could tell you how much the total amount of star formation is in the universe today. And I'll show you a plot in a second, but it's actually not very much. There's not that much star formation going on today. And so we would like to know, has the universe always been this way? Is this actually a lot of star formation and there was even less in the past? Or was there more in the past and the universe is really just winding down its star formation? And so for that, we really need very deep imaging to see further away. So I'm going to introduce to you here a plot that I'm going to show a number of times during this talk, showing you the history of star formation in the universe. Okay, so I'll reveal the axes one at a time for maximum excitement. So the vertical axis here is showing the amount of star formation in the universe from a lot at the top, things like the antennae galaxies, to not a lot at the bottom, things like M87, where there's really zero star formation. And really, this is the amount of star formation in some volume. So let's just say the entire universe. And the number doesn't really matter, but we're going to go from a lot to not very much. And on the horizontal axis, we have time. So here we are today, and I'm plotting it in these weird units, time since the Big Bang. So the Big Bang is the event that formed our universe. It happened about 13.8 billion years ago, so it's kind of over here. And then we're over here at 13.8. It's plotted in log scale, so you can see I stretch it. So the first billion years takes up a lot. That's because that's the most exciting part. And the last 12.8 billion years takes up not so much, but that's okay. Finally, on the bottom vertical axis, or sorry, horizontal axis, is something we call redshift. So we mentioned that everything is moving away from us, and that's causing everything to look redder than it otherwise should be. We can measure that shift, that red shift, how much the light of these galaxies are shifted to the red, and we can assign a number to it. And that's what this means here. And you can see that redshift goes hand in hand with time since the Big Bang. And so I'll shout out some redshift numbers from time to time, but I'll also try and remember to give you the time since the Big Bang, since that's a handy reference. All right, so let's look at the state of the art in the early 90s. So around the time Hubble was launched, what had we learned? Well, we had only learned this little bit. We'd only been able to study galaxies out to about a redshift of 1, which is about 7 or 8 billion years into the past here. And we learned, and we learned that although today there's not that much star formation, 7 or 8 billion years ago, there was actually quite a bit, almost a factor of 10 more. So as we go back in time from today, the universe is forming more and more stars, okay? And so that's key to know. So we've got this wonderful telescope, this Hubble Space Telescope, just launched a few years ago. We're pretending we're in the 1990s, remember? Just launched a few years ago, got its mirror fixed, as Fritz told us about. So why not just point it and stare nowhere for a week, okay? What could we actually learn? Well, we could learn what happens to this total amount of star formation in the universe. Does it keep going up? Does it keep going down? Or does it do something a little bit crazy, okay? And there are ideas. You could find a theorist that would tell you anything. I don't know if you could find a theorist that would tell you it would do this weird little cyclical thing, but there were the reasons to believe it could keep going up or keep going down. So this was the thinking behind the Hubble Deep Field. So the image on this shirt, but not the words on this shirt. So this was actually the subject of an Astronomy on Tap talk a couple of years ago, which remains one of my favorite Astronomy on Tap talks. So good that I put the link here at the bottom. And this was conceived through hallway conversations at the Space Telescope Science Institute. This was called a director's discretionary program, where Hubble stared at a carefully chosen patch of blank sky, for about 10 days. And the area of this tiny patch of sky was about 1/140th of the full moon, okay? And so they said, let's just stare at this place and see what we see. And as you can imagine, it may have been a little controversial, let's say, because Hubble is really hard to get time on views. There's lots of cool things people want to do with the Hubble. And if you're saying, I want to stare at this tiny patch of sky where I don't know that anything is there for 10 days, you must be crazy. And so the only way this would happen is if the director of Space Telescope Science Institute used his time. The director of the institute owns about 10% of the time to do this. And so that's what happened. And here's the wonderful image. Okay, so this again comes from about 1996. This beautiful color image was made from images taken in 4 filters from the near ultraviolet to the near infrared. So wavelengths we can see from the ground, optical, but also wavelengths we needed to see from space using the Wide Field Planetary Camera 2. So this was the new camera that was installed on Hubble when they fixed the flaw in the mirror. And it's beautiful. You're taking a region of the sky where you thought there was nothing, and it's just filled with galaxies. And we'll zoom in there. And you can see galaxies of all shapes. You have spirals, like we could see in the nearby universe, and maybe ellipticals, but then some irregulars, that thing here, this weird thing going on there, and then all these tiny little dots, which are really, really, really distant galaxies. All right, so it's filled with galaxies, and long story short, we found galaxies out to a redshift of 4, or a time about 12 billion years after the Big Bang, or 11.5 billion years into the past. And so we're seeing pretty far back. And when we place the results on this curve, this red line is where we were before the Hubble Deep Field. And we can see, no, it didn't keep going up. No, it didn't keep going down. It actually stayed pretty straight and maybe just starts going down above a redshift of 3, but it's kind of hard to tell. It certainly looks like there was a peak in the cosmic star formation activity around 10 billion years or so ago. Awesome, awesome stuff. But of course, you're like, well, there's still 2 billion years of universe to go before that between these observations and the Big Bang. What happened? Did it stay high? Did it dive off a cliff? Did it jump up really high? And of course, for that, we're going to need more observations. So one thing the Hubble Deep Field did is it created an industry of blank field imaging surveys where you say, aha, we're going to stare at this blank field. We don't know what's there, and we're going to learn a lot of stuff. And that went from controversial to mainstream very quickly. So our story picks up in 2002 when astronauts on board the Space Shuttle Columbia, this is actually Columbia's last successful mission, made a number of improvements to the Hubble Space Telescope over 5 spacewalks, including the installation of a new camera, the Advanced Camera for Surveys. This was an optical camera, just like with PIC2, but it had much better sensitivity in the near infrared, making it possible to discover even more distant galaxies. And soon after this was installed, there were 2 new programs which used this ACS camera to study the distant universe. One called the Great Observatory's Origins Deep Survey, or GOODS. Astronomers love their acronyms. This was a little bit different than the Hubble Deep Field. Instead of staring at one place for 10 days, it said, let's stare at one place for 5 hours, but actually then stare next to it and next to it and next to it and make a big region of the sky. So GOODS actually looked over 2 separate fields, which when combined, covered an area of the sky about 32 times that of the Hubble Deep Field. So we're looking at a much wider part of the sky. But at the same time, we of course wanted to see what happened if we took this brand new camera, ACS, and stared at the same patch of sky. And so a different program, the Hubble Ultra Deep Field, my favorite image, did a similar observation as the Hubble Deep Field, but because it's with this new camera, it actually went much deeper. And so this is not a beautiful image, but this is actually an image I had on my hard drive. This is a GOODS image of one of the 2 GOODS fields called the GOODS South field. And this is about 16 times the area of the Hubble Deep Field, okay? And you can see there's one region here that looks a little bit cleaner. That's actually where the Hubble Ultra Deep Field is. It lies within this GOODS field, and we will zoom in there. And you can see that's beautiful. It's filled with galaxies. I'll show you a color image in a minute. But I want to give you an example of why you actually needed to do these 2 surveys. This is actually a cutout of this image at the overlap, where here is the GOODS depth, which is a few hours, and here is the Hubble Ultra Deep Field depth towards the upper left, which is several days. And you can just see how the noise level, that background static in there, goes way down. And all of these little faint things that you couldn't see in a few hours, all of a sudden pop out. And so one of the things we've learned from these type of surveys is that doing what we call wedding cake style surveys, going wide and shallow and narrow and deep and building your wedding cake, is a great way to learn all kinds of things about the distant universe. So here's the image. This is my actual favorite version of the Hubble Ultra Deep Field image because of the way the colors really, really pop in here. And I'll just zoom in. And you can see that there are a wide variety of galaxies again, but we're seeing them in even more glorious detail than we were able to see with the Hubble Deep Field. All right, so what did we actually learn from this? Well, remember from the Hubble Deep Field, we went out to a redshift of 4, which was about 2 billion years from the Big Bang. With the Hubble Ultra Deep Field and with GOODS, we can go out to a redshift of 6, about 1 billion years after the Big Bang. So of that remainder of the unexplored territory, we got half of it already with this camera. And we'll go back to our handy plot. And these colored symbols here, they show us where these new results were at. And you can see that no, the cosmic star formation rate does not stay in a straight line. It really does peak around redshift 2, or at a time about 10 billion years into the past. And then it declines. And it looks like it's declining kind of steadily, but it's hard to tell because, again, there's still a lot of time out here, a whole billion years of the universe that we don't know about. So Hubble had one last trick up its sleeve to try and push that cosmic horizon further closer to the Big Bang. During the final servicing mission in 2009, I can't believe that was 11 years ago now, astronauts added one final new camera, the Wide Field Camera 3, or WFC3, which, among other things, had the best ever near-infrared sensitivity in a space telescope. They also revived ACS. It had actually died a little bit before the launch, and they were able to revive it. They had to actually unscrew things and make repairs. These were things that were not designed to be repaired in space with astronauts in these big, bulky spacesuits and bulky gloves, and they did an awesome job accomplishing everything on that mission. But I'm going to focus on this Wide Field Camera 3 because it allowed us to go to even higher redshifts or the more distant universe. And so what did we do? You can probably predict what astronomers do. We did what we do best, which is made up more acronyms. Specifically, we designed CANDLES, which is the Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey. CANDLES imaged an area 150 times that of the Hubble Ultra Deep Field with WFC3, and all of that area was also imaged with ACS. So we had optical and near-infrared imaging. We imaged the Hubble Ultra Deep Field, that same region that had that beautiful ACS imaging. We imaged it in the near infrared with Wide Field Camera 3, and actually 2 different surveys, adding deep imaging as red as Hubble can go. And then a few years after that, the Hubble Frontier Fields came along that did imaging to the depth of the Hubble Ultra Deep Field, but on top of galaxy clusters, these beautiful metropolises of the universe, which have so much mass and such a small volume, they actually act as cosmic magnifying glasses and lens or magnify background galaxies, letting us see things that are otherwise too faint to be seen with Hubble. And so this is a nice family picture of the CANDLES field. So CANDLES imaged 5 separate fields around the sky, including the 2 GOODS fields here, adding 3 other ones, COSMOS, UDS, and EGS. EGS I'm very partial to because this is the field we're going to be studying with the James Webb Space Telescope in the survey that Michaela mentioned. And I'm showing you here where the Hubble Ultra Deep Field sits in good south. So this is great. This is the base layer of our wedding cake, wide, but kind of shallow. So of course we want to go deep in the Hubble Ultra Deep Field. So this is showing the near infrared version of the Hubble Ultra Deep Field in the middle. And each of these little boxes is around a very distant galaxy that our team discovered. It's actually in 2010, right soon after these data came public. I was actually showing these to my daughter who you saw, and she pointed out one of these and she's like, that image is really ugly, Dad. Why didn't you do better? And I was like, well, you know, this is several days with the best space telescope we have. So I think we'll take it. And finally, a couple of years later, like I mentioned, the Hubble Frontier Fields came along, and this is an image of one of the galaxy clusters that the Hubble Frontier Field Survey did. All of these big yellow galaxies here, those are the galaxy cluster galaxies. They're relatively nearby. They're at redshift 0.4 or so, but these stretchy snake-looking things, those are very distant galaxies that are being magnified and stretched out, so we can study them in more detail. And so when we take all of these new surveys together, we kind of hit the limit of what Hubble can do. But we have been able to find galaxies out to a redshift of 10, or a time only 500 million years after the Big Bang, or that should say 13.2 billion years into the past, 13.3 billion years into the past. And here is what we see. This is the picture we have today. Cosmic star formation starts at kind of a low level. As we go into the past, it reaches a peak about 10 billion years ago. And then as we reach towards the Big Bang, it declines, and it looks like it declines pretty smoothly. Again, we don't know what's happening in this first 500 million years, but we've learned a ton so far with Hubble. But of course, we always still have more questions. Specifically, if we look at the data points, they agree pretty well. But as you get out towards redshift 10, they start to be spread out quite a bit, where some studies find, oh, there is actually maybe quite a bit of star formation at redshift 10, where maybe you could draw a straight line through this, like this blue line. And some studies find more like that, this dashed purple line, oh, there's actually a turnover in the star formation rate density, and it kind of starts diving off a cliff. These lines here are actually from theoretical models with realistic physics in them, and they can actually explain both types of observations. And so we don't actually know what's right. The only way to know what's happening is to actually go out and observe and put some data points on here. But for that, we need redder imaging. And unfortunately, as Fritz mentioned, Hubble is not going to be serviced again, and so that's not going to be Hubble. But fortunately, NASA has something else in its pipeline, which is the James Webb Space Telescope. So James Webb has a mere 7 times larger in area than Hubble, so we can see much fainter objects. But it's also prioritized for the infrared. And so it's going to be very sensitive to infrared light. We'll be able to see much redder than Hubble. Unfortunately, this is not a real image. Webb is not in space. It's actually sitting right now in Redondo Beach, California, in a clean room north of Grumman. But as of today, its launch is set for less than 1 year for today, March 31st, 2021. I wouldn't quite hold us to that yet. As with everything, they've been quite a bit delayed from the COVID-19 situation. There are still some people allowed to work on it, but most people are only allowed to work from home for safety, of course. So depending on how things shake out the next few months, it might see a few month delay. Hopefully, but hopefully by next summer, we will see this telescope in space. And so I just wanted to finish up showing you what Webb can do. So again, here's my favorite image, the Hubble Ultra Deep Field. I said it's filled with galaxies, right? But let's be nitpicky. If we look around the image, we can find spaces that are blank. There's no galaxies here. There's no galaxies here, 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 here. Now that I'm looking for them, it's all over the place. So what's going on? Have we seen the limit of galaxies? Is there really nothing there? Or are there galaxies there that are just beyond the reach of Webb? And using our best guess at what is happening, we can actually make a simulated Webb Ultra Deep Field image. And this is what we think it will look like. And you can see that all those blank dark regions where there were nothing are now filled with galaxies. They're tiny, they're small. We can only see them with Webb, but we think they're there. We just need this fabulous new telescope to find them. And so with that, I will end. Thank you.
Thank you, Steve. I got to finish chugging this beer because of all that. I also want to give a bit of a shout out to Jackie's talking head comments earlier.
My audio is messed up. There we go.
Can you hear me?
That's back. Yes, now I can.
Yeah, shout out to Jackie's talking head comment earlier. Since you blend in with all the galaxies in your background, you are a talking head right now.
There we go.
So thanks for talking about some of the really cool stuff that we get to study, and we do have some questions for you. So we're gonna start off with one from Pete Roche, which I enjoy because it's kind of what we're doing. So the question is, how will JWST advance our understanding of when reionization happened and how it has evolved?
Ooh, good question. So reionization was the subject of Astronomy on Tap talk I gave maybe a year ago or so. It's on YouTube somewhere. So reionization is the time when the first stars and galaxies in the universe turned on and energetic photons from those galaxies ionized gas in between galaxies. So even though the space in between galaxies looks empty, it's actually filled with ionized gas. That gas today has all lost its electrons. It's all ionized. And we know that that had to happen at very early times. So what will Webb do? Webb is going to allow us to see the beginning of reionization. And so we spend a lot of time trying to study the end of reionization today, redshift 6, 7, 8 with Hubble. But we really need more sensitive imagers, more sensitive spectrographs to see what's going on at redshift 10. We have this big disagreement now, so we don't really know. And maybe even go to redshift 12. So as Rebecca can tell you, we're trying to study early reionization now with current telescopes, and it's very, very, very difficult. And so Webb will provide a huge advance there.
Would you say it's accurate that we are currently pushing the limits of Hubble's capabilities in order?
I would say that's accurate.
So Hubble is amazing, but we also need more things. So we will not mention that word, but our next question is from my friend Charlie. Since it's a deep field, do we think any of the galaxies we're observing this far out still exist?
Yeah, good question. So when we look at these really distant galaxies, we're not seeing them as they are today. We're seeing them as they are at some point in the distant past. So let's take that most distant example I gave, that redshift 10 galaxy. It looks like a tiny little dot in our image, right? And it's probably pretty blue. It's kind of hard to tell because we can just barely see it. That tiny dot today probably lives inside something like M87, that big honking yellow, big massive ball of stars today. Because that tiny dot we can barely see with Hubble, that is one of the most massive galaxies that exist at redshift 10. We can only see the biggest, brightest ones. And that's one of the things Webb will do, is let us go fainter. And if it's the most massive thing then, it probably lives inside the most massive thing now. So some of the stars that existed then certainly exist today, but the galaxy is going to look much different.
So it's now part of a larger galaxy.
That's right.
Right. All right. So we are going to continue to ask some questions. now that we've had enough to drink to talk about James Webb, what are some of the things that you're most excited about finding with the James Webb Space Telescope?
Redshift 12 galaxies.
What is redshift?
Or redshift 15 galaxies.
Oh my God.
So
Okay, what is that?
I showed that plot of star formation, and there's some models that say it goes down and some says it goes really smoothly. I have like reason to think that maybe the smoothly one is more real, but maybe that's too much of a hunch. So we really need to get data to find out what's happening. And so this early release science program that Michaela mentioned is designed to find up to 50 redshift 10 galaxies and hopefully 5 to 10 redshift 12 galaxies. And so we'll find the most distant galaxies that humans have ever seen. And even more important, we will constrain these models of star formation in early galaxies to let us know exactly how different these galaxies were than galaxies today.
So what would that tell us about us and where we are now?
Ooh, well, when I think about why is this interesting, I think that humans are often interested with where we came from. Where did humans came from? How did the Earth form and evolve? This question is really centered around how did the Milky Way form and evolve? And so if we want to understand how the Milky Way came to be, you could study that in a variety of ways. And one of the ways that we do it is by looking for galaxies at a variety of distances and figuring out how galaxies evolve with time. And so we'll really learn how the earliest phases of galaxies like the Milky Way happened.
I find this fascinating. Obviously, that's why I do that work. Michaela, did you have anything you'd like to ask?
No, I just want to give a shout out to my dad for that reionization question.
Nice. I'll give a shout out to my dad, who is wearing an Astronomy on Tap shirt. He sent me a picture of it.
I love it.
And my whole family. I don't want them to get mad. My whole family too. Hi, family.
I believe your sister was on earlier, Steve. All right. So I think at this point, we're probably going to bring back the rest of our speakers because we have some questions that we haven't asked. So we're going to end our show with a little bit of a wrap up, and then we'll go on to questions. So if you have asked a question and we haven't answered it yet, please repost it in case we missed it. Also, if there's any other questions you have for us, post those in the chat right now, tag us wherever on social media, and we'll pay attention to that. And so Michaela and I will do a little bit of a closing, and then we will start to address those questions. So go ahead and start sending those in. So we have too many buttons to push after enough to drink.
Everything's open still.
Aha. Cool. Great. Nope. Wrong button. Okay, go.
So you have been hopefully playing trivia throughout the evening, listening to our speakers' talks and finding the answers to the questions in their talks to get all your trivia questions right. Usually at the end of our live shows, we go through the answers to the trivia questions and announce the winners, but we are hoping that some people who couldn't make it tonight will still want to watch our show over the next couple of days. So we will keep trivia open until Friday night, and we will announce the answers and the winners at the end of the week. So last time it took us like several days to get to it, but we're on top of it this time. So check back in on our social media accounts. We'll post the answers and we will contact the winners through email. And remember, you don't have to get everything right to possibly win. So definitely play.
Okay, so I remembered to grab the thing, what's this called? Coffee mug. We're doing great. I remember to grab the coffee mug. And so this is what we'll be sending you with, oh my God, too many things. With the coasters that we have. So these are both made by Odell Brewing Company, and they're amazing, and they have a really cool logo for you. And please fill out the trivia. Let us know if you have any questions, comments, or anything that you'd like to see on the show. And again, I want to give a big thanks to all of our speakers tonight. You guys did a great job. To all of our space cadets, everyone who's behind the scenes that you don't necessarily see on the camera. It's a whole committee of us, and you see some of them active in the chat, and I really appreciate all the things that you're doing, Sam, Andrea, Logan, all of you back there behind the scenes making this possible for us, to our committee for helping us put the show on, and again, to our venue, the North Door. We really appreciate all of the things that you have done to house us for the past 5 years. And hopefully if when all this is over, we'll be right back there again. And so if you do have the ability, please go ahead and help them out. The link will be in the description and again in the chat. And most of all, thank you to you guys. Thank you for encouraging us to continue doing this show. It's a lot of work and it's a whole new world for us, but I hope that the live streams are exciting and fun. And I'm glad that people from more than just Austin get to come watch the show. So thank you for showing up.
Rebecca's really good at jumping the gun on this, but again,
I forget there's a slide for it. I'm sorry.
It's great. No, it's perfect. We really do want to support our venue, our wonderful venue, and the people who work there. So if you haven't already, or even if you had, if you're willing to give a couple of dollars, that would be awesome. We pass it on to them, and it really does make a big difference. And they're very appreciative and excited to get this support from the community.
So next month is May, and it is graduation. Although that looks very strange for some of our undergrads, we still want to showcase some of the amazing research and the work that's being done by undergraduate students here at UT and elsewhere. So we're doing another special undergraduate show this May on May 19th at 7:30 p.m. in the same location you're at right now, potentially in your living room. So AoTATX number 68 will happen May 19th, 7:30 p.m. here on this channel. We're going to talk about some of the research undergrads are doing and any kind of interesting prospects they have going forward after they graduate.
That is definitely going to be a good show to tune in for. Our undergrad show last year was very possibly one of our most acclaimed of the whole year. So put it on your calendars, and I hope you can join us.
Shout out to Logan for doing our undergrad show last year. Now she's a grad student in Tucson. She's currently the space drafts person on the chat. We miss her, and she's now doing Astronomy on Tap in Tucson. And so we're glad that she can come be part of our show with us tonight. Speaking of other Astronomy on Tap locations, you can check out any of the other Astronomy on Taps around the world at astronomyontap.org. We are not the only show that is online. We are doing our videos as normal now on the third Tuesday of the month, but there are a lot of locations that, since you can now watch online, have a bunch of videos up for you. So go ahead and check that out on the website that has information for you. Also, take time to connect with us on social media. We're trying to be more active and engaged in between shows for you. We have YouTube for you to watch any of our previous talks. I know Steve mentioned a couple of them, and we put those links in the chat. We have Facebook and Twitter and Instagram and an email. And if there's something we're missing, please God, don't say TikTok, then we'll try to do all of those things. Please connect with us, send us a shout out, and don't forget to share your favorite Hubble image with us.
And I think that's it for the official show. So now we'll ask all of our speakers to come back if they're still around, and we can start asking some of these extra questions that we have.
Perfect.
Awesome. Yay. Okay, so I would like to start this off with a question that we have actually for all three speakers. So this question is from Julie, and she asks, what is the most unexpected thing you found with Hubble data? So I guess, Fritz, we can start with you.
Last month, I actually measured the mass of a planet orbiting Proxima Centauri. That was totally unexpected because I wrote a paper saying there wasn't anything there 20 years ago with the knowledge. We had new knowledge now, so no, that was it. It's great.
So why not go look when you get new
Exactly. No, somebody had to do it. I mean, the data's there. Somebody said, well, hey, this planet exists or it doesn't exist. Well, if it exists, it should show up in our data, and it did. So that's great. That was unexpected.
Hashtag science. I love how science works.
It is wonderful how science works.
Excellent. Laura?
Yeah, this is an easy one. I was part of a team that discovered a planet evaporating by accident. It was led by a grad student at the time, Jessica Spake, and she was looking for water in the planet's atmosphere and instead found at this really specific wavelength that the planet's radius was way larger than we expected, several times the normal radius of the planet. And she emailed me and she said, Laura, like, can you look at this data? I'm seeing something really weird. And I said, sure. And I looked at it and I found the same thing she did, but what I told her was that cannot possibly be right. Like, sure, the Hubble is broken or something. We'll figure it out. But she was really persistent, and she realized that we were seeing helium that was evaporating from the planet's atmosphere, and we just didn't know what to look for, which is very typical, I would say, of the study of exoplanets, that every time we open our eyes and look for something, we see something new and often surprising.
The most important phrase in science is, huh, that's funny.
Yeah, it was definitely, I mean, that's better than what I did. I was like, nah, can't be. It turned out to be really interesting.
That's very, very cool. Steve?
Yeah, so I think the most surprising thing for me has been that not only can we find galaxies out to these amazing distances and amazingly early times, it's that there are a lot of bright ones. And so it's something that a number of us in our group are studying right now, is trying to figure out exactly what the abundance of really bright galaxies at these early times are, and then trying to understand how does the universe make a really bright massive galaxy in a really short period of time.
I like that question because I'm also working on it. Let's see. Sorry, we're scrolling through quite a...
Yeah, there's a lot of things to be looking at right now. Okay, we have some questions specific for specific speakers. So Laura, we have some questions for you. Would you be able to answer Hector's question about if it's possible for a planet to have a further Goldilocks zone if it's tidally locked to their star, effectively having like one side that's hospitable while not necessarily having the other side hospitable?
Yeah, that's a great question. And there's been some conversation of like a habitable ring, like at a very specific spot on the planet. And yeah, I would say the jury's still out. Like it's tricky to keep one isolated part of your planet habitable, because if there's water there, it might flow somewhere else and freeze or evaporate. But yeah, that's definitely an idea that people think about.
Also, do you know if for tidally locked planets, are the habitability odds good on the night side? So the day side will be warmed up by the actual star, but what about on the night side? Is it going to just be conditional on the distance, or is that something that's not possible?
Yeah, it really depends on, there's all kinds of factors that will make a difference. Like the thickness of your atmosphere matters. If you have a lot of atmosphere, it can help circulate energy to the night side. If you have an ocean, that can help circulate heat to the night side too. And yeah, I'm not a modeler myself, so my answer is always, let's go out and observe these planets and see what we can learn about them. But yeah, it's really definitely, if you have a tidally locked planet, that really changes the temperature structure compared to what you would have for a planet like Earth.
Be a whole different kind of world. All right, Michaela, did you want to ask some of the news questions?
Yeah, I was just going to say, I have a question for Jackie. Oh, yeah. So Cam asks, quoting you, I think when you were talking about the superclusters, but I don't actually remember, the most massive gravity-bound objects in the universe. So that was the quote. And the question is, are there larger non-gravity bound objects in the universe that we know about?
Yeah, so I saw that question and I went way too hard on answering it. I actually have a slide for you. So
Nice.
You made a
way
slide
more.
during the show?
No, but I had a slide that was
Excuse
relevant.
me? Hello?
What the heck? I'm barely like reading comments and doing the show at the same time.
Okay,
How
so
many
here's
windows do you have open?
so many. Okay, so this is from a talk that I gave to the department yesterday, actually. So it was on my mind. So you asked, are there larger gravitationally bound objects than galaxy superclusters? And the answer is no, because there is no single object that is that massive. What I meant was that superclusters have a combined mass of something like 10 to the 15 solar masses, but that's including all of the individual galaxies that are bound and orbiting each other, and it also includes its dark matter halo. So you can actually see this visually through a dark matter simulation, which is why I pulled up this slide. So this is called the cosmic web. As dark matter evolves over time, it forms into a denser and denser knot like filament network. And then you get these galaxy superclusters in the most massive gravitationally bound dark matter halos that are that massive, because about 90% of the matter inside these clusters is dark matter. So that's your extremely detailed answer. You're welcome.
That was above and beyond.
I don't know how to get out of this now. The end.
Wow. Okay. Thank you. Danny, we had a question during your news segment. Are planets and their atmospheres predictable based on the metallicity of their stars?
So, I mean, I can talk a little bit about planets and metallicity of the stars. We do see trends with planet occurrence and metallicity. And I mean, if Laura, if you want to chime in at all, if I say anything wrong, that would be appreciated. But right, I believe that it is true. We've found more. The occurrence of gas giant planets, I believe, increases with increasing metallicity. I don't know if there is a trend for smaller planets. I don't know if we have enough statistics for that. But atmosphere-wise, I don't know if we've studied enough atmospheres to also understand statistics with metallicity. Is that right?
Yeah, that's a great job. We know for sure that there's strong positive correlation with stars that are more metal rich forming more giant planets like Jupiter. And for smaller planets, it looks like there's little to no correlation. In terms of whether the atmosphere of the planet is more metal rich around a more metal rich star, there are just results starting to come out about that now. And it looks like there's no correlation, which suggests some fairly stochastic behavior, like a lot of randomness in what you end up with for your planetary atmosphere coming out of a cloud of gas where the star came from. It's not necessarily tied to the stellar composition.
Looks like we have a ton of planet questions, but we do have one kind of galaxy question, and I'm going to regret asking this. But Steve, speaking of James Webb, what's the latest on the launch?
So the latest on the launch is that it is on schedule for March 31st of 2021, which is less than 1 year away. As of a week ago, there was still about a month of contingency left in the schedule, meaning they could do nothing for a month, and then they could pick right back up and nothing else went wrong. It would launch on time, so that's promising. But a lot of the things that need to be being done are simply not being done because many people are not allowed back at work. So we will see. The good news is, unlike a mission that's going to a planet where there are very tight launch windows because planets, like move, the place where Webb is going in space is kind of moving around the sun with us. So it can launch most times. So a 2-month delay in kind of packing everything up and getting it ready to go, hopefully will translate into something like a 2-month delay in the launch. The only other mitigating issue is the launch site, Kourou, in South America, which is where the European Space Agency launches things, and they are in charge of launching our beautiful telescope. It has also not been launching things, and so there's probably going to be a backlog. I just imagine all these like rockets lined up ready to go, even though I'm sure it looks nothing like that. So uncertain if you know, we can really clamp this thing down and get back to work in the next month. Maybe it can launch on time. Otherwise, maybe by mid-2021, we will see.
Oh man.
For once, it's not our fault though.
True. At least this was not in a user error, so to speak.
Right.
All right, so some more planet questions. But first, we have a couple questions for our speakers, especially those with virtual backgrounds on. Occasionally, Steve, a little circle pops up above your head and people want to know what is behind you. Laura, what is the print behind your head? So whoever would like to share where they're sitting right now.
I love that these are the questions that are coming up.
Inquiring minds want to know.
This behind me is it's a Picasso print. He did a whole bunch of lithographs of toreadors, and I saw it at an antique shop and I loved it, so I bought it.
I like it a lot. It's really cool. Steve, what's the circle above your head?
So I had no idea that was happening until my wife, Silver Surfer, also Astronomy on Tap speaker, told me when we were ending and I went to say goodnight to my kids. I think it's got to be that I moved the monitor a little bit from where it normally is so my kids can be seen, and there's that little mirror that's now above my head. And I think the facial recognition Zoom software must have kept getting confused about it. But I had the artificial background on, so you wouldn't see, I don't know what's behind me. A recording sign that we put on the door so people don't budge in when we're recording our lectures. That's about it. That's interesting back there.
By people, you mean the children?
Oh, and there's a sword. It's Ned Stark's sword.
Okay. Winter has already come. All right. So exoplanet questions. When in your talk, Laura, you showed a plot of like the transit of a planet, and so you show there's one big dip, and then there's a second shallower dip. And what does that represent? Is that when the exoplanet is traveling behind the star? Is that like some kind of loss of the signal that way, or how does that work?
That's right. Yeah. As soon as your planet goes behind the star, then any light from the planet, either heat being emitted or reflected light off like clouds in the atmosphere, is blocked. And so you're seeing that loss of any light coming from the planet when it goes behind the star.
Another question, could there be atmospheres with higher concentrations of oxygen than nitrogen? And if so, would that affect the habitability?
Oh, that's a great question. And I think, sure. I mean, for a planet like Earth, there are many factors that shape the atmospheric composition, everything from outgassing from volcanoes to delivery of material from comets, all kinds of stuff. And so the exact mixture and the presence of life. And so the exact mixture of gases depends on all of that. And you could definitely end up with a different oxygen nitrogen ratio. As far as life goes, I would say ask a biologist about that. It depends so much on what kind of fuel the life would need. We see life on Earth that doesn't need oxygen, that can live on like geothermal vents in the deep ocean. And so there's all kinds of different things that bacteria or more complex life can use for fuel.
We're back to that. It's a controversial question, the habitability of planets.
Yeah, definitely. And a lot of it is like couched in our understanding of life as we know it on Earth. And so there's always this lingering question of like, what about life as we don't know it? What kind of variety is there? And if there's any lesson to take away from exoplanets, is that there's a lot of variety. Our solar system is pretty small.
Steve, we have actually a question for you too. If you could design your perfect telescope, what would it be and why? Would it be Hubble? Would it be Webb? Or would it be something else?
Louvoir.
Yeah. So if we are sticking to the limits of like modern technology and what we can build, so NASA has form teams to explore what the next space telescope would be. So Webb is the next space telescope. The next one is WFIRST, which is the Wide Field Infrared Survey Telescope, which is kind of the same size as Hubble, but with a really big field of view. And then the next one hasn't been decided yet, but we're hoping to kind of figure that out soon. And they're all good. Don't get me wrong, they're all good. My personal favorite is LUVOIR, another acronym, the Large Ultraviolet Optical Infrared Telescope. It is kind of like Hubble, but instead of being 2.4 meters in diameter, which I can almost do with my arms, it's 15.1 meters in diameter. So it's like the mirror is like the size of a house, and it will be able to see so far away and see things in such great detail. It'll be super awesome. But if the imagination is the limit, 1,000-meter space telescope, I mean, that's, yeah. We'd have to build that one on orbit, but that's okay.
Interferometer on the moon.
Yeah, I was waiting for you, Jackie.
Yeah. If you like the radio.
Ooh, shots fired.
I like radio.
We have
never going to get all the time again.
All right, we have a question for Fritz. So at the beginning of your talk, you mentioned, or maybe you mentioned, could you talk a little bit more about the corrections that had to be made to Hubble so it could see? And would it have been able to do anything without correcting it?
Yeah, it could have done some things without correcting. Could have done the astrometry, the measurement of star positions, but then they wouldn't have supported that because they didn't launch it to do that. They launched it to do the other science that it should do. So the corrective lens is basically, I take my glasses off and I can see kind of, but not really very well. And I put my glasses on and I can see very well indeed. And so what the first servicing mission did was basically bring the telescope back to where it should have been originally. And that was wonderful, and it happened. So without that, they just shut it down. Literally, I'm sure they would have. They just said, we can't spend that money on that. We'll have to, we just eat that loss, and that's it. So that would have been horrible. And I'll tell you, for about 2 years, I lived in mortal fear of that. I mean, I had a job working with Hubble Telescope, and is it going to go or not going to go? And it almost didn't. But that was not the first time. There were so many times when you guys with your JWST horror stories about, oh, it's going to get canceled or this is going to get canceled. Hubble Space Telescope from 1960 until it finally launched every 2 years was on the chopping block. And I was too stupid to realize that. I was fat and happy. I'm working on Hubble. And nobody told me that I was going to go away, maybe.
A little reassuring that we're not alone in this.
That's
field.
right. I feel your pain.
I mean, my PhD got switched to something else. So, thank God for tech time. Okay, so on a happier note, we have some other questions. So Cass has texted some questions to us asking about the James Webb Space Telescope. So first I'm going to drink to that actually happening on that note. So will it actually be able to focus on intrasolar objects? Like, can we get detailed close-ups of our planets, their moons, and then what's the actual type of radiation that it looks at or wavelength of light? Anybody can jump in and answer that.
I can say a little bit. Yeah, Hubble can definitely look at stuff in the solar system. JWST. One of the challenges is that solar system objects are so bright. So you have to sometimes be really creative by looking at like light bouncing off of another object so you don't fry the detectors. And in terms of wavelength coverage, it goes from optical 0.6 micron, 600 nanometers that we can see with our eye, all the way out to, you can do photometry all the way out to 28 microns. So it's a huge wavelength range, and that infrared wavelength coverage is really critical to a lot of new science cases. Particularly for me, if I'm interested in looking at heat coming from cool exoplanets, that happens out at really long wavelengths. And so that's one of the science cases I'm the most excited about.
That's awesome. I do believe it's also looking at volcanoes on Io. a moon of Jupiter that's erupting a lot of things. So Danny, I don't know if you want to chime in on the solar system moon concept here, but I think because volcanoes are like hot things and infrared is like heat signatures in space, we'll be able to actually look at volcanoes on moons of our own planets in our solar system.
Yeah, that would be cool. Yeah, I don't know. I feel like I've read a little bit about, or I tried to read up a little bit if James Webb was gonna do anything with the icy moons in the outer solar system, and I'm not sure. Right? I mean, those moons, it's just tough because they're so close to their host planet, which is so bright. So I don't know if I don't know what they could do, but yeah, I mean, heat signatures like that would be really interesting. And on any of those moons, there are areas of activity which would be hotter than the rest of the surface that would be interesting to look at.
So one of the early release science programs is observing the solar system. It's observing the Jupiter system.
Okay.
We'll observe some of the moons as well. I didn't know that. I just Googled it.
I would also mention that, so I went to like a workshop where they teach you how to use JWST for different science goals. And it was really cool and exciting because I learned a lot about not my science, which is galaxies. And the solar system observations with Webb, and I'm sure Hubble, were some of the most complicated because it never occurs to me that your target might be moving like faster, you know, like a galaxy is sure moving, but so far away that we would never see it. But, you know, if you're trying to observe Io, it was very interesting to plan an observation with a telescope on something that's moving so fast. That was kudos to everyone who does that.
Yeah, it turns out like nearby things move. That's complicated and difficult and very overwhelming. And so much math, Danny, I don't understand.
I was observing at Keck once, and the second half of the night I was observing were observing Saturn, and they couldn't find it. And I remember looking through the window and being like, it's right there, I can see it.
Was that actually helpful?
Just
no,
use
not like me.
I'm a TA for the observational course that Steve actually teaches. And one time one of the students asked me, what's the RA index of the moon? And I stopped and thought about it, and I was like, everywhere at some point, I think.
That is the correct answer to that question.
It goes around. All right, so Fritz, just out of curiosity, so when Hubble got delayed, let's say, from being able to do some of its full science, what did you manage to do in those few years? Did you find some other kind of science? Was there other data that you had? What were you doing with your time while you were waiting for it to get fixed?
What a great question. And I have to remember back to the 80s. So it's like if you lived through the 60s, you don't remember it, right? I lived through the 80s, and I think that the delays were such that NASA would cut a check every 2 years, and then we get paid. And basically what we were doing is making sure that the telescope would do what we wanted it to do. For instance, the fine guidance sensors. They had to point to within 7 milliarc seconds or something like that. And people cared that that was the case, but we cared that it actually could do 1 milliarc second, because that was our science. And so we would go to meeting after meeting after meeting, and the people at PerkinElmer who were building the fine guidance sensor would say, well, we could save some money if we didn't do this, but then we'd be back to 8 milliarc seconds, and we'd scream bloody murder and yell and throw the science case at them again. And they would change their mind finally, because NASA told them to, because the astrometry science team, which was there to do science, astrometric science with Hubble Space Telescope, said, no, that's not good enough. So that was most of the 80s, I think. I mean, the Challenger disaster, I mean, I was in an airport going to a meeting, a Hubble Space Telescope meeting, when I'm walking through the airport and there's this stuff on the TV screens at the thinking, good God, that can't be true. And I called my wife at home and I said, did that really happen? And yes, it happened. So there was another delay. I mean, there were years with Hubble Space Telescope, we were in what we call an infinite slip mode, where every year we'd lose a year and a half or something. So it's looking like we would never get launched, but we in fact finally did get launched. Although I went to the launch, and 3 minutes before the launch, they said APU malfunction, that's auxiliary power unit malfunction, and they did not launch. So I went home, and 2 weeks later they finally launched, but I didn't even get to watch it.
Oh, that's
So,
awful.
rats.
Oh man. I feel like I want to go see the launch of JWST, but I don't know if I can handle that.
Yeah,
I
right.
couldn't even handle watching the documentary with Steve Squires about a Mars rover that I know made it to Mars. But when they cut to him watching the launch and it doesn't go, I'm like, oh my God.
It's too much stress. It's so much stress.
It is stress, I'll tell you.
Oh my God.
But then what a great way to end that story with 30 years of amazing science. Just
It
gotta not end it on a
No,
right.
and
Let's be positive.
right. Well, this is when people were trying to chop JWST, and they say, "Oh, well, you know what it's going to do." Well, Hubble was a fine example of that. We didn't know what Hubble was going to do. It sure as hell did some great stuff, and so will JWST. So don't chop it; just make it work. But now I'm expressing my worry because, like, you mentioned the Mars landing in the 7 minutes of terror. And I first saw that. I saw the animation. I said, oh, that's never going to work. There's going to be a new crater on Mars. So then it worked. And so now when I watch the JWST deployment, I think to myself, yeah, that could happen.
God, I don't have another beer, you guys. It's terrifying. It's gonna work. It's gonna be fine. It's gonna work.
I hope so, because y'all are very brave, and we were all very brave to hang with Hubble, and just got to be brave.
I don't know if brave is what I want to have to be.
not being positive. You
You
were
want to
very
be
brave.
successful.
All right, we were being positive. It's gonna work.
And you were being brave with Hubble, and it was amazing and paid off and gave so many decades of amazing science.
Yeah, that's right.
Here's to that.
No,
Yeah. Happy birthday, Hubble.
Yes, cheers.
here's the Hubble.
Here's to Hubble.
All right. I think we have one last question, unless we've missed some along the way. And I don't know what this was in reference to, but I assume we're just going to ask a generic question. Is there life on exoplanets somewhere out there in the universe?
Yes, of course.
Go, anyone.
It's such a waste of real estate if there's not.
I feel like this is a gotcha. Like now we're being recorded. I would not personally be doing this if I didn't believe there was life on other planets. I'll answer it that way.
That's a good answer.
Yeah, to elaborate just a tiny bit, like there are, like if you look at the numbers, there's 300 billion stars in our galaxy. Most of those stars have planets. A lot of them are habitable, probably, in terms of the size of the planet, the temperature of the planet. We're talking about tens of billions of potentially habitable planets in our galaxy alone. And there's hundreds of billions of galaxies. So these numbers are really mind-boggling. And we know that water is common. We've seen it on a lot of other planets. And so I would be shocked if there was not at least one other one that had suitable conditions for life to evolve. And our job now is to try to find those.
I agree. And I think the major issue is it going to be non-microbial? Is it going to be something that we could communicate with which we could communicate? That's the big question for me. I mean, life is ubiquitous in the galaxy, I'm sure, but are there advanced life forms that we could communicate with? That's the issue for me.
I think with the numbers of stars and planets, it's got to be there. But the galaxy is so big that It doesn't have to be close by.
Yeah, yeah, yeah. The time to say hello and have them say hello back is far longer than the lifetime of any civilization that we know of.
Yeah, it turns out time is not in our favor here. Space is incredibly big, you guys, like so big. And so like light only travels at a finite speed. Like they said, saying hello will take some time to get to the next star, would take 4 years. And then even if they deciphered a message and they lived there and they were a communicable civilization, had technology and ways to communicate with us, it would still take another 4 years for that to get back to us. So now we're talking about an 8-year turnaround on a simple hello message. And I don't know about you, but our world changes on smaller scales than that. So not entirely sure where we'll be in 8 years or if we'll be able to carry on any kind of conversation. Did you guys have any last thoughts, comments, musings about the Hubble Space Telescope, or things you'd like to say about the 30th anniversary, or anything before we turn off the stream?
Well, for me, it was absolutely astonishing that it's still working after 30 years. Every aspect of the telescope, from design to execution to launch to using, except for about 2 years, everything always was better than anybody ever promised. The results were always better than people thought they would be. So it's a wonderful engineering thing is to under promise and over deliver, and Hubble did that, and I'm just so happy that I got to play with it. I mean, I tell people, ask me, what do you do for a living? I work with Hubble Space Telescope. It's like getting paid to play with electric trains. I mean, it's just, it's fun.
It's cooler than that.
It's far cooler than playing with electric trains. It's just
an electric space machine.
That's right. And to be able to say, huh, that's funny, or gee, nobody's ever seen that before, and I'm the guy who gets to see it, or my team gets to see it. It's just, it's wonderful. I mean, it's the joy of science. That's why we do it.
Steve.
That's why you're sticking with it, right?
It's absolutely why we're here.
As big a pain in the rear end as it is.
Oh, yes. Steve, did you have any comments?
I'm always amazed at how much of my research centers around Hubble Space Telescope data, because it's so hard to get a hold of it, but there are so many wonderful surveys. And one of the big things actually that these blank field imaging surveys I talked about did is they really made mainstream the idea of public surveys, that if you're going to use a big chunk of the telescope, then you don't get to keep the data to yourself for a year. Everybody gets to get it on day one. And that's really made a lot of the science that I've been able to do possible. And it's really made that sort of the main way in which these big surveys are going to happen into the future with other telescopes.
Laura, did you want to say anything at all?
Happy birthday to Hubble. 30 is not so bad, turns out.
Yeah.
So young.
Yeah, I think I am going to sign off. I'm on East Coast time, so it's getting a little late for me.
Perfect.
But thanks so much for having me on the show. This was super fun.
So glad that you were able to come and join us. Again, all of her information for everybody watching is in our YouTube description and in the comments. Please follow Laura and all the amazing science that she's doing. And we're very excited that you could join us. Thankfully, we are a little bit virtual, and so that we don't have to have people actually physically located in Austin at our Austin show. So thank you for joining us from Boston and from the Harvard CFA.
My pleasure. Stay safe, everybody.
All right.
Bye.
All right. On that note,
The same goes true with all of our speakers. We have their information, websites, social media in the YouTube description, and links. All the links are there to check them out after.
Yes, follow all of us on social media, and we will continue to try to bring space to you. I don't think we have anything left. I think we've answered all the questions that we had. Thank you for everyone tuning in. We will be here May 19th, if I remember the date properly, for our next show. It's the third Tuesday of the month. We're back on schedule. We're happy and we're live. We don't know if we're going to continue to do a live stream from our venue once all of this is over. I know there are people who are asking about that. We do put our YouTube videos up on our channel.
We're catching up. We're catching up.
Yep, it's happening. They're being edited, so they will be up, and we'll be posting those as soon as we have them, so that even if you aren't able to watch the show locally, that you'll be able to see all of our talks and the things that we do. Hopefully soon after they happen, going on in the future. Cheers to Hubble. One last time, happy birthday. Let us know if you have a favorite Hubble image. Post that, tag us, let us know, and we'll share it. Thanks to Danny and Jackie for doing an amazing segment in the news, Fritz and Steve for giving great talks, and always Michaela, my amazing co-host, wrapping astronomy on tap in your house. Super excited.
Thank you, Rebecca.
Thank you all.
Yeah, thank you.
Bye, everyone. Have a great
Bye.
night.